teaspoon of neutron star weighs 6 billion tons. That is not a metaphor. That is not an exaggeration for effect. That is the actual measured density of an object sitting in our galaxy right now, roughly 20 kilometers wide, spinning hundreds of times per second, and casually violating every intuition you have ever had about what matter is supposed to do. These things should not be stable. They should not hold together, and they definitely should not be sending signals toward Earth that we cannot explain, but they are. Right now, a pulsar called Geminga is bombarding our planet with antimatter. Positrons, the mirror image twins of electrons streaming toward us from 800 light-years away. For years, scientists thought dark matter was responsible. They were wrong. It was a dead star. Meanwhile, 15,000 light-years from here, an object named GPM J1839-10 has been pulsing a radio signal every 22 minutes for at least 33 years. No neutron star we know of should be able to do that. The physics does not allow it. The rotation periods are wrong, the magnetic fields do not match, and yet the signal keeps coming, regular as a heartbeat, defying every model we have. And then there are the explosions. Luminous fast blue optical transients, events 100 times brighter than supernovae that flare into existence and vanish within days, leaving almost no trace. Some astronomers think neutron stars might be involved. Others have no idea what is happening. This is not a story about objects we understood and filed away. This is a story about the universe's most extreme laboratories, the places where gravity bends space-time so violently that light itself struggles to escape, where a single cubic centimetre contains more mass than a mountain, and where the signals we're receiving right now are rewriting the rules we thought were solid. Welcome to Space Dust. If you're new here, please subscribe. We make these documentaries every day and we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in for a great journey. A star does not go gentle into that good night. It burns through its fuel with the kind of reckless confidence that comes from having millions of years and a core temperature measured in tens of millions of degrees. But the fuel does run out, and when it does, what happens next makes every nuclear weapon humanity has ever built look like a match strike. This is the story of what comes after. Of the objects left behind when the universe's largest furnaces finally go cold, of neutron stars, the densest stable objects in the known cosmos, and of the fact that even now, decades after we discovered them, we still cannot fully explain what they are doing or why some of them are sending signals we have no model to account for. Stars are fusion reactors. That's not a metaphor. They sustain themselves by squeezing lighter elements into heavier ones, releasing energy in the process. In the core of a star like our Sun, hydrogen fuses into helium. The energy released pushes outward, balancing the crushing inward pull of gravity. As long as that balance holds, the star lives. But massive stars, the ones with 8 or 10 or 20 times the mass of our Sun, do not stop at helium. Once the hydrogen in the core is exhausted, the core contracts and heats up until it is hot enough to fuse helium into carbon, then carbon into neon, neon into oxygen, oxygen into silicon. Each stage burns faster than the last. Hydrogen fusion can sustain a star for millions of years. Silicon burning lasts about a week. The star is now running on borrowed time. And the clock is ticking faster than anyone standing on a planet orbiting that star would ever suspect. Silicon fusion produces iron, and iron is where the party stops. Not because iron is special in some mystical sense, but because of basic nuclear accounting. Every fusion reaction before iron releases energy. Fusing iron costs energy. There is no profit. The core fills with iron ash, piling up like spent fuel rods in a reactor that cannot be refueled. Gravity does not care about your energy budget. It has been waiting patiently for billions of years, held at bay by the outward pressure of fusion. The moment that pressure drops, gravity moves in. Fast, the core collapses, not over months or days, over seconds. In less time than it takes to read this sentence, a ball of iron the size of Earth compresses down to the size of a city. The temperature spikes into the hundreds of billions of degrees. Electrons are forced into protons, producing neutrons and releasing a flood of neutrinos. Those neutrinos, which barely interact with normal matter under any circumstances, are produced in such overwhelming numbers that they carry away most of the energy of the collapse. They stream outward through the outer layers of the star like ghosts walking through walls. Behind them, the collapsing core slams to a halt, not because it wants to, because it has hit a wall built out of quantum mechanics. The wall is called neutron degeneracy pressure. Here is the short version of why that matters. Neutrons, like electrons, are fermions. Fermions obey something called the Pauli exclusion principle, which is a fancy way of saying that no two identical fermions can occupy the same quantum state. Squeeze them close enough and they resist, not because of any force in the traditional sense, but because the rules of quantum mechanics forbid them from being compressed any further. In a collapsing stellar core, once the density hits about 10 to the 12th grams per cubic centimetre, neutron degeneracy pressure kicks in. The core stops collapsing. The infalling outer layers of the star, which are still rushing inward at a significant fraction of the speed of light, hit that rebounding core and bounce. The rebound tears the star apart from the inside out. The explosion is a Type II supernova. For a few weeks, that dying star can outshine its entire host galaxy. What is left behind, buried in the expanding cloud of debris, is the core. A ball of neutrons roughly 20 kilometers across, a neutron star. Let's talk about density. Because this is where human intuition breaks down completely. Neutron stars are dense in a way that has no everyday comparison. The numbers are so extreme that they stop meaning anything until you anchor them to something tangible. The average density of a neutron star sits somewhere around 6.7 times 10 to the 17th kilograms per cubic meter. Different sources give slightly different ranges depending on the equation of state they are using, which is physicists speak for the model that describes how matter behaves under these conditions. Some estimates land closer to 3.7 times 10 to the 17th. Others push up to 5.9 times 10 to the 17th. The exact number depends on how deep you're measuring and what assumptions you're making about the internal structure, but those are just numbers on a page. Let me give you a picture. Take a teaspoon, the kind you use to stir your coffee, fill it with neutron star material. That teaspoon now weighs about 6 billion tons, not 6 billion pounds. 6 billion tons. That is roughly the mass of Mount Everest compressed into a volume you could balance on the tip of your finger, assuming your finger did not immediately vaporize from the gravitational field or collapse into a microscopic crater under the weight. You could fit about 1,000 teaspoons into a gallon. A gallon jug of neutron star material would weigh 6 trillion tons. That is more than all the water in all the oceans on Earth, in a jug. This density is not just extreme by the standards of everyday life, it is extreme by the standards of atoms. Ordinary matter is mostly empty space. An atom is a nucleus surrounded by a cloud of electrons, and the distance between the nucleus and the electrons is enormous compared to the size of the nucleus itself. If you scaled a hydrogen atom up so that the nucleus was the size of a marble, the electron cloud would extend for several kilometers. Inside a neutron star, that empty space is gone. The atoms have been crushed out of existence. What is left is essentially one giant atomic nucleus. The neutrons are packed so tightly that the density approaches, and in the very core may exceed, the density of an atomic nucleus itself. That density is about 10 to the 14th to 10 to the 15th grams per cubic centimetre. For reference, water has a density of 1 gram per cubic centimetre. Lead is about 11. The centre of the Earth, under all the crushing pressure of thousands of kilometres of rock and iron, tops out at around 13. Neutron star material is 100 trillion times denser than that. The collapse that produces this object happens because iron cannot fuse. But why does the core stop at neutrons? Why does it not keep collapsing all the way down into a black hole? The answer is neutron degeneracy pressure, but there is a subtlety here worth unpacking. Under normal conditions, a free neutron is unstable. Leave a neutron sitting by itself in empty space and it will decay in about 15 minutes, splitting into a proton, an electron and an antineutrino. This process is called beta decay. Inside a neutron star, beta decay does not happen. Not because the neutrons are special, but because there is nowhere for the decay products to go. The core is so dense and so tightly packed that adding another proton and electron to the mix would cost more energy than the decay would release. The neutrons are stable not because they want to be, but because the alternative is energetically forbidden. This is degenerate matter. The neutrons are not bonded together the way atoms in a molecule are bonded. They are simply crushed into the same space, held there by gravity, and prevented from collapsing further by the fact that quantum mechanics will not let them occupy the same states. The result is an object that defies every intuition we have about what matter should be able to do. Neutron stars are small. 20 kilometers across is about the size of Manhattan. Our Sun, by comparison, is about 1.4 million kilometers across. You could fit more than 1 million Earths inside the Sun. A neutron star, despite being smaller than a city, weighs about 1.4 times the mass of the Sun. That mass-to-size ratio produces a gravitational field so intense that it warps spacetime into a steep, nearly vertical well. Escape velocity at the surface of a neutron star is about 1/3 the speed of light. Light itself, which climbs out of the Sun's gravity well without breaking a sweat, has to work to escape a neutron star. Photons leaving the surface lose energy to the gravitational field, shifting toward redder wavelengths by the time they reach us. And it gets stranger, because neutron stars do not just sit there, they spin. Fast. Some of them rotate hundreds of times per second. The fastest known neutron star, catalogued as PSR, J1748-24468, spins 716 times per second. That is faster than a kitchen blender. A point on the equator of that neutron star is moving at roughly 1/4 of the speed of light. The reason they spin so fast is conservation of angular momentum. Before the core collapsed, it was rotating slowly as part of a much larger star. When the core shrank from the size of a planet to the size of a city, its rotation sped up the same way an ice skater spins faster when they pull their arms in. Except instead of a skater, you have a ball of neutrons the mass of the Sun spinning faster than any human-made object has ever moved. That spin, combined with the intense magnetic field carried over from the original star and amplified by the collapse, turned some neutron stars into cosmic lighthouses. The magnetic field channels radiation out along the magnetic poles, and if those poles are not aligned with the spin axis, the beams sweep across space like searchlights. If one of those beams happens to point toward Earth, we see a pulse of light every time the star rotates. We call those pulsars. And the precision of their pulses is so stable that when they were first discovered in 1967 by Jocelyn Bell Burnell, the initial hypothesis was that they might be artificial, signals from an alien civilization. The discovery team briefly labelled the first pulsar LGM-1 for little green men. They were not aliens, they were neutron stars, but the fact that trained astronomers initially considered an artificial origin tells you how strange the signals were. Nature does not usually produce clockwork that precise. Pulsars are not the only strange thing neutron stars do. Some of them produce bursts of X-rays, some emit steady beams of gamma rays, some flicker and stutter in ways no model fully explains. And some of them, as we will see, produce signals that should not be possible under any theory we currently have. But before we get to the signals, we need to understand what it would be like to stand on one of these objects. Not that you could. Not that anything made of atoms could survive the experience. But as a thought experiment, it is worth walking through. Because the environment on the surface of a neutron star is so extreme that it makes the core of the Sun look like a pleasant afternoon. First, the gravity. At the surface of a neutron star, gravitational acceleration is about 200 billion times stronger than on Earth. If you somehow had a body that could withstand that, which you do not, you would be flattened into a layer of atoms less than 1 millimeter thick. Your constituent particles would be compressed so tightly that the distinction between you and the ground would cease to exist. You would not die. You would stop being a distinct object. Mountains on a neutron star, if they exist, are measured in millimeters. The crust is thought to be incredibly rigid, possibly the strongest material in the universe, but even that crust cannot support a feature more than a few millimeters tall before the weight crushes it back down. The surface is not made of rock or metal in any sense you would recognize. The outer crust is thought to be a crystalline lattice of iron nuclei, packed into a solid structure and held together by a sea of degenerate electrons. Go deeper, and the pressure increases. The nuclei become more neutron-rich. Eventually, neutrons start dripping out of the nuclei, forming a neutron fluid that coexists with the lattice. This is called the neutron drip line, and it marks the boundary between the crust and the deeper layers. Below that, we enter territory where theory becomes uncertain. The inner crust and outer core are thought to contain exotic states of matter that cannot be reproduced in any laboratory. Neutron superfluids, proton superconductors, possibly quark matter, where the neutrons themselves have been squeezed so hard that they dissolve into their constituent quarks. No experiment on Earth can recreate these conditions. The only place they exist is inside neutron stars. Which means every observation we make of a neutron star is a glimpse into physics we cannot test any other way. And now the signals, because neutron stars are not silent. They are not inert. They are active, dynamic, and in some cases deeply strange. The pulses we detect from pulsars are the most famous signals: steady, predictable, reliable. But there are others, signals that arrive irregularly, signals that last for milliseconds and then vanish, signals that repeat on timescales that make no sense, and signals that seem to be coming from objects that according to our model should not be capable of producing them. This is where the mystery begins, not with the density, not with the spin, not with the magnetic fields. Those are extreme, yes, but they fit within the framework of known physics. The signals, on the other hand, do not. Some of them sit right at the edge of what our theories allow, and some of them sit beyond that edge, in a space where we do not yet have a map. Standing in a field on a quiet night looking up at the stars, you would never guess that some of those points of light are the remnants of explosions so violent they briefly outshone billions of suns. You would never guess that scattered across the galaxy are objects so dense that a handful of their material weighs more than a mountain. And you would never guess that some of those objects are sending signals toward Earth that we have been recording for years without fully understanding what they mean. Neutron stars are not rare. There are thought to be about 100 million of them in the Milky Way alone. Most are invisible to us, too faint or too far away to detect. But the ones we can see, the ones that happen to point their beams in our direction or flare up in X-rays or collide with a companion star, those ones have given us a catalogue of phenomena that keeps growing faster than the explanations. The gravity alone would kill you 1,000 different ways before you ever touch the surface. That is not an exaggeration. That is physics, the kind that does not care about your intentions or your spacecraft's shielding, or how carefully you plan the approach. Get within a few thousand kilometers of a neutron star and the tidal forces start pulling you apart. Get closer, and the distinction between pulling and shredding stops being meaningful. Let's put a number on it. The surface gravity of a neutron star sits at roughly 200 billion times the gravitational acceleration you feel standing on Earth right now. 200 billion G. That is the kind of number that stops sounding like a measurement and starts sounding like a punchline. But it is real. It has been measured indirectly through observations of how neutron stars affect their surroundings, how they bend light, how fast material spirals into them before impact. For comparison, Earth's surface gravity is about 9.8 meters per second squared. A neutron star's surface gravity is somewhere in the neighborhood of 10 to the 12th to 10 to the 13th meters per second squared, depending on the star's exact mass and radius. The variation comes from the fact that not all neutron stars are identical. Some are slightly more massive, some slightly larger. But the range does not matter for what happens to you. In every case, you are obliterated. Here is what that means in practice. Imagine you are falling toward a neutron star. You are in a hypothetical indestructible spacesuit because we are going to need to pause the part where you vaporize for a moment to talk about the gravity itself. You are falling feet first, which is the worst possible orientation but also the most illustrative. Your feet are closer to the neutron star than your head. That means your feet are experiencing stronger gravity than your head. On Earth, that difference is negligible. On a neutron star, it is not. The gravitational gradient, the rate at which gravity increases as you get closer, is so steep that the pull on your feet compared to your head becomes enough to stretch you. This is called a tidal force, and it is the same effect that causes ocean tides on Earth, just scaled up by a factor that makes the comparison almost meaningless. As you fall closer, the difference in gravitational pull between your feet and your head grows. Your body starts to elongate, not all at once, slowly at first, then faster. The tissues in your legs are pulled downward harder than the tissues in your torso. Your spine stretches, your bones begin to separate. This process has a name in astrophysics: spaghettification. It is not a joke term, it is the actual word used in peer-reviewed papers to describe what happens when tidal forces stretch an object into a long, thin shape. By the time you are within a few hundred kilometers of the surface, You're no longer a human body in any recognizable sense. You're a stream of atoms still loosely organized in the shape of a very long thread, but no longer held together by molecular bonds. Those bonds snapped thousands of kilometers ago. But let's say, for the sake of the thought experiment, that you somehow survive that. Let's say you are made of something that cannot be spaghettified, some kind of exotic matter that does not care about tidal forces. You are still falling, and you are accelerating. Neutron stars have escape velocities of about half the speed of light. Some sources put it closer to 0.6 times the speed of light, roughly 180,000 kilometers per second. Escape velocity is the speed you need to leave a gravitational well without using any additional thrust. It is also, by conservation of energy, the speed you will be travelling if you fall in from a great distance. So you're now moving at a significant fraction of the speed of light. At those speeds, the air resistance analogy breaks down because there is no air, but if there were, you would ignite. As it is, even the stray hydrogen atoms floating around in the space near the neutron star are hitting you with enough energy to generate heat. Lots of it. You're not falling anymore, you're a relativistic projectile. Then you hit the surface, or more accurately, the surface hits you. Because from your perspective, the ground is rushing up at a sizable chunk of light speed. The impact does not feel like anything because the moment of impact is over faster than any nerve signal could ever travel. You do not splat. You do not even compress. You convert. Your kinetic energy, all of it, turns into heat and radiation in a region of space smaller than the period at the end of this sentence. If you were somehow watching from a safe distance, you would see a brief flash of gamma rays. That is all that is left. That is what remains of a human body after it falls onto a neutron star. But let's rewind. Let us go back to before the impact, back to the point where you are somehow still intact and hovering, impossibly just above the surface. Let us talk about what that surface actually looks like and what it does to the space around it. The surface of a neutron star is smooth. Not smooth in the way a marble is smooth. Smooth in the way a geometrically perfect sphere is smooth. The gravity is so intense that it crushes any deviation from perfect flatness almost immediately. Mountains, if they exist at all, are measured in millimeters, not kilometers, not meters, millimeters. This was not obvious at first. Early models of neutron star structure assumed that, like planets, neutron stars could have some surface topography. Hills, ridges, maybe even something resembling tectonic features where the crust buckled under stress, but the math does not support it. The gravitational field at the surface is so strong that even the rigid crystalline crust, which is thought to be the strongest material in the universe, cannot hold up a feature more than a few millimeters tall. Some studies have put the limit even lower. A paper published in 2021 calculated that mountains on neutron stars might be restricted to fractions of a millimeter. To put that in perspective, the Himalayan mountain range on Earth rises about 9 kilometers above sea level. The tallest known mountain in the solar system, Olympus Mons on Mars, is about 22 kilometers high. A neutron star mountain, by comparison, is roughly the height of a grain of sand. Why does this matter? Because the smoothness of a neutron star's surface is a direct consequence of how gravity warps spacetime around it. Gravity is not a force in the traditional sense. It is the curvature of spacetime caused by the presence of mass. The more mass you pack into a given region, the steeper the curvature. A neutron star packs 1.4 solar masses into a sphere 20 kilometers across, which means the curvature near the surface is extreme. Think of spacetime as a rubber sheet. Place a bowling ball on the sheet and it sags, creating a dip. That dip is gravity. Roll a marble near the bowling ball and it curves toward the dip following the curvature of the sheet. That is an orbit. Now imagine placing a bowling ball so heavy that the sheet does not just sag but folds almost vertically. That is a neutron star. The curvature is so steep that objects near it do not gently curve inward. They fall. That curvature does something strange to light. Light travelling near a neutron star does not move in straight lines. It bends following the curves in spacetime. If you were standing on the surface of a neutron star, assuming you could stand, and assuming your eyes still worked, you would see something deeply wrong with the sky. First, you would see more of the star itself than should be geometrically possible. Normally, standing on the surface of a sphere, you can see roughly half of it. The other half is behind you, blocked by the curvature of the surface. But on a neutron star, the gravity bends light so severely that photons emitted from the far side of the star curve around and reach your eyes. You would see the back of the star in front of you, distorted into a ring of light wrapping around the horizon. This is gravitational lensing, and neutron stars are some of the most extreme lenses in the universe. Second, the stars in the sky would not be where they appear. Light from distant stars, bent by the neutron star's gravity, would arrive at your eyes from the wrong direction. The constellations would be unrecognizable. Some stars would appear in multiple places at once, their light split into separate paths by the warped geometry of spacetime. Third, time would be wrong. General relativity predicts that clocks run slower in stronger gravitational fields. This is not a metaphor or an approximation, it is a measurable effect. GPS satellites orbiting Earth have to account for it, or their clocks drift out of sync. On the surface of a neutron star, the effect is extreme. For every second that passes for you on the surface, more time passes for an observer far away. Exactly how much more depends on the mass and radius of the star, but the difference can be significant. Minutes for you could be hours for someone watching from orbit. This is called gravitational time dilation, and it means that escaping a neutron star is not just a matter of overcoming gravity. It is a matter of climbing out of a region where time itself runs slower. If you could somehow leave the surface and return to a safe distance, you would find that more time had passed for the outside universe than for you. You would have aged less than the clocks around you, not by much probably, but by a measurable amount. And escaping is not an option. The escape velocity, as mentioned, is about half the speed of light. No chemical rocket can reach that speed. No ion drive, no nuclear pulse propulsion, nothing we have ever built or seriously proposed comes close. The only way to leave a neutron star is to already be moving faster than any human-made object has ever moved. Which means if you fall in, you're not coming back out. Even light struggles. Photons leaving the surface of a neutron star lose energy to the gravitational field. This is called gravitational redshift. A photon emitted in the ultraviolet might arrive in the visible range. A photon emitted in the visible range might arrive in the infrared. The deeper the gravitational well, the more energy the photon loses climbing out. Astronomers see this redshift in the spectra of light from neutron stars and use it to estimate how strong the gravity is at the source. Now let's talk about what happens to matter that actually reaches the surface. Not hypothetical indestructible matter, real matter. Atoms, molecules, the stuff planets and people are made of. As material falls toward a neutron star, it accelerates. By the time it is close, it is moving at a substantial fraction of the speed of light. When it hits the surface, the kinetic energy converts into heat. A lot of heat, enough to ionize the atoms, strip the electrons away and smash the remaining nuclei into the crystalline iron crust. The surface temperature of a neutron star can vary depending on its age and how much material is currently falling onto it, but typical values sit around a few million degrees. That is hotter than the core of the sun. The infalling matter does not just heat the surface. It briefly becomes the hottest thing in the immediate region, emitting X-rays and gamma rays before the energy dissipates. If the neutron star is accreting material steadily, from a companion star in a binary system for example, the impacts produce a continuous glow of high-energy radiation. The more material falls in, the brighter the glow. In some cases, the buildup of material on the surface can trigger runaway nuclear fusion, producing a sudden explosion called a Type 1 X-ray burst. These bursts release as much energy in a few seconds as the sun emits in a week. The crust itself is not passive. It is under immense pressure, squeezed by the gravity above it and the even denser layers below. The outer crust is thought to be a solid lattice of iron nuclei, the most stable configuration at those densities. Go deeper, and the pressure increases. The nuclei become more neutron-rich, absorbing free neutrons from the surrounding electron sea. Eventually, at a depth of a few hundred meters, the pressure becomes so high that neutrons start dripping out of the nuclei altogether. This is the neutron drip line, the boundary where the nuclei can no longer hold themselves together. Below that, the crust transitions into a strange state where neutron-rich nuclei coexist with a fluid of free neutrons. The neutrons flow through the lattice like water through a sponge, and the properties of this neutron superfluid are still not fully understood. The inner crust and outer core are even stranger. The free neutrons are thought to form a superfluid, a state of matter with zero viscosity that can flow without friction. The protons, which are still present in smaller numbers, may form a superconductor, a state where electrical current flows without resistance. Both of these phases are predicted by quantum mechanics, but they have never been observed in a laboratory because the conditions required to create them are impossible to replicate on Earth. Go deeper still, into the core, and we enter territory where even the theoretical models start to disagree. Some models predict that the neutrons remain intact, held together by the strong nuclear force in a kind of neutron soup. Others suggest that at the extreme densities in the core, the neutrons themselves break apart into their constituent quarks, forming a quark-gluon plasma. A third possibility is that strange quarks, which are heavier and less stable than the up and down quarks that make up protons and neutrons, become stable at these densities, forming strange matter. Strange matter is hypothetical. If it exists, it would be more stable than ordinary matter under the right conditions, which raises a disturbing possibility. A neutron star with a core of strange matter would not be a neutron star anymore. It would be a strange star, an object where the transition from neutron matter to quark matter has propagated outward from the core. And if strange matter is truly more stable, then a collision between a strange star and a normal neutron star could convert the normal neutron star into strange matter as well. The process would be irreversible. We do not know if strange stars exist. We have no confirmed observations of them. But the fact that they are allowed by the equations is enough to keep physicists awake at night. The mountains, such as they are, sit on top of all this. The crust, despite being the strongest material we can imagine, cannot support anything tall. The calculations that led to the millimetre-scale mountain limit are based on the tensile strength of the crust and the gravitational stress trying to flatten it. The crust can withstand enormous pressure, but even it has limits. Exceed those limits and the crust fractures, releasing energy in the form of a starquake. Starquakes are real, we have detected them. When the crust of a neutron star cracks and shifts, it releases a burst of energy that shows up as a sudden change in the star's rotation rate and a spike in X-ray emission. The most famous example is the Magnetar SGR 180620, which produced a starquake in 2004 so powerful that it briefly saturated every X-ray detector in the solar system. The energy released in that event was equivalent to what the Sun emits in 250,000 years, and it happened in 1/10 of a second. The mountains, if they exist, are probably not static features. They are more likely to be transient bulges in the crust caused by magnetic stresses or by the buildup of material from accretion. Over time, gravity wins and flattens them back down. The surface of a neutron star is dynamic, constantly reshaped by the forces acting on it, but always trending toward perfect smoothness. Now imagine you are hovering above this surface. Not on it, because that would be instant death, but a few meters above, suspended by some impossible technology. You're looking down at a sphere roughly 20 kilometers across, glowing white-hot from the residual heat of its formation. The surface is so smooth it looks polished, with no visible features except for the faint patterns of iron nuclei crystallized into a lattice so rigid it makes diamond look like tissue paper. The horizon is close, much closer than it would be on Earth. Stand on Earth, and the horizon is about 5 kilometers away, depending on your height. Stand the same height above a neutron star, and the horizon is less than 6 kilometers away, just over the curvature of the star's surface. The sphere feels small, claustrophobic in a way that is hard to articulate. You're standing on an object the size of a city that weighs more than the sun. Above you, the sky is chaos. The stars are bent, distorted, smeared into arcs by the gravitational lensing. Some stars appear twice, their light split into two paths by the curvature of space-time. Others are stretched into rings, Einstein rings, where the light wraps completely around the neutron star before reaching your eyes. The Milky Way, if you can even recognize it, is twisted into shapes that bear no resemblance to the view from Earth, and below you the surface is pulling, not gently. Not the way Earth pulls on a dropped object. This pull is violent, relentless, patient in the way a black hole is patient. It does not need to reach up and grab you, it just waits. And the moment your impossible hovering technology fails, the moment you drift even slightly closer, the tidal forces begin their work. You do not fall. You are drawn in, stretched, compressed, heated and disassembled at the atomic level before you ever reach the surface. The atoms that used to be you slam into the crust at a fraction of the speed of light and vanish into the lattice, adding an infinitesimally small amount of mass to a star that will not notice the difference. This is not a place where humans, or anything like humans, can exist. It is not a place where chemistry as we understand it functions. The gravity is so strong that it overrides the electromagnetic forces that hold atoms together. The matter here obeys different rules, follows different equations, exists in states that we can only describe mathematically because we have no physical intuition for them. And yet neutron stars are common. There are 100 million of them in the Milky Way. They are not exotic outliers or rare cosmic accidents. They are a natural consequence of stellar evolution. Every massive star that has ever lived and died left one behind, or in some cases, collapsed even further into a black hole. They're out there, scattered across the galaxy, spinning in the dark, waiting for something to fall into them, or for something to push them into our line of sight. Some of them are loud. They emit beams of radiation that sweep across space like lighthouse beams, pulsing with a regularity that rivals the best atomic clocks humanity has ever built. Those are the pulsars, and they are the reason we know neutron stars exist at all. Without those beams, most neutron stars would be invisible, too small and too dim to detect at interstellar distances, but the beams give them away. And the beams, it turns out, are just the beginning. The first pulsar was discovered on November 28, 1967, by a 24-year-old graduate student named Jocelyn Bell Burnell. She was working at the University of Cambridge under the supervision of Anthony Hewish, who had built a radio telescope specifically designed to detect quasars. The telescope was enormous, covering more than 4 acres of countryside, and it was made of wood and wire strung between posts. It looked less like a precision scientific instrument and more like a field full of clotheslines. The telescope worked by detecting faint radio signals from space and printing them out on rolls of paper. Lots of paper. Every day, the telescope produced about 96 feet of chart paper, covered in squiggly lines representing the intensity of radio signals at different times. Bell Burnell's job was to analyse those charts by hand, looking for anything unusual. On a chart from late November, she found something that should not have been there. A small section of the trace showed a series of rapid fluctuations, a bit of what she later described as scruff. It was faint, easy to miss, and it did not look like any known source of radio noise. She marked it and kept going. The signal showed up again a few weeks later, same location in the sky, same pattern. Bell Burnell asked for a higher speed recording of the region, and when the data came back, the team saw something that stopped them cold. The signal was not random noise. It was a series of pulses, each one lasting a few hundredths of a second, repeating with clockwork precision every 1.3 seconds. The regularity was unsettling. Natural processes in space tend to be messy. Stars flicker. Galaxies vary in brightness. Even the most stable cosmic objects show some irregularity when you look closely enough. But this signal did not flicker or vary. It ticked. Over and over, one pulse every 1.3 seconds, with a precision that made the team briefly wonder whether they had detected something artificial. They labelled the source LGM-1. LGM stood for Little Green Men. It was a half-serious designation, the kind of shorthand scientists use when they are not sure what they are looking at but need to call it something. The possibility that the signal was extraterrestrial was on the table, not because the team believed it, but because they could not immediately rule it out. Hewish later said that the regularity was so perfect that the team considered whether it might be a beacon from an alien civilization. Bell Burnell herself was less excited about that possibility. She was in the middle of writing her doctoral thesis, and, by her own account, was annoyed at the idea that her work might be derailed by Little Green Men. She wanted to finish her degree, not spend the next year fielding questions about aliens. Over the next few weeks, the team worked to eliminate other explanations. Could it be interference from a passing satellite? No, the signal stayed fixed relative to the stars, not the Earth. Could it be a reflection of a terrestrial radio source bouncing off the moon, or a nearby object? No, the timing ruled that out. Could it be an instrumental artifact, some quirk of the telescope producing a false signal? No, they checked the equipment and found nothing wrong. Then Bell Burnell found a second source. Different location in the sky, different pulse rate, then a third and a fourth. Whatever these objects were, they were not unique. They were a class, and they were natural. No one was building radio beacons and scattering them across the galaxy. The team published their findings in February 1968 in the journal Nature. The paper introduced the word pulsar as shorthand for pulsating star, though at the time they were still called rapidly pulsating radio sources. The discovery made headlines. Scientists around the world scrambled to find more of them. Within months, dozens of pulsars had been identified. Within a few years, the count was in the hundreds. Today, we know of more than 3,000. The explanation for what pulsars actually are came quickly. A neutron star, as we have established, is a dense ball of neutrons left behind after a supernova. But neutron stars are not featureless spheres. They have magnetic fields, extremely strong magnetic fields. Stronger than anything we can produce in a laboratory, stronger than anything found anywhere else in nature except possibly in magnetars, which are neutron stars with magnetic fields so intense they deserve their own category. The magnetic field of a typical neutron star clocks in at around 1 trillion Gauss. For comparison, the Earth's magnetic field is about half a Gauss. A refrigerator magnet is about 100 Gauss. An MRI machine pushes up to about 30,000 Gauss. A neutron star's field is 1 trillion, in some cases a quadrillion. The field is so strong that it affects the behavior of atoms near the star, distorts the vacuum of space, and channels the radiation emitted by the star into narrow beams that shoot out along the magnetic poles. Here is the key point. The magnetic poles of a neutron star are not aligned with its rotation axis. Just like Earth's magnetic north pole does not sit exactly at the geographic north pole, a neutron star's magnetic axis is tilted relative to the axis it spins around. So as the star rotates, the magnetic poles sweep around with it, and the beams of radiation emitted from those poles sweep across space like the beam of a lighthouse. If one of those beams happens to point toward Earth, we see a flash of light. Then the beam sweeps past and the light cuts off. Then it comes around again and we see another flash. The result is a pulse. Not because the star is turning on and off, but because the beam is rotating in and out of our line of sight. This is the lighthouse model, and it explains almost everything about how pulsars behave. The pulse period is simply the rotation period of the star. A pulsar that flashes once per second is a neutron star spinning once per second. A pulsar that flashes 10 times per second is spinning 10 times per second. The fastest known pulsar, catalogued as PSR J1839-10 AD, spins 716 times per second. That neutron star completes more than 700 full rotations in the time it takes you to say the word rotation. The beams themselves are produced by charged particles, mostly electrons and positrons, accelerating along the magnetic field lines near the poles. As those particles spiral around the field lines at relativistic speeds, they emit synchrotron radiation, a type of electromagnetic radiation that can range from radio waves to X-rays depending on the energy of the particles and the strength of the field. Most pulsars are brightest in the radio part of the spectrum, which is why radio telescopes are the primary tools for finding them. But some pulsars also emit visible light, X-rays, and gamma rays. The reason pulsars spin so fast goes back to conservation of angular momentum, the same principle that makes an ice skater spin faster when they pull their arms in. Before the supernova, the core of the star was rotating slowly as part of a much larger object. When the core collapsed down to the size of a city, its rotation sped up dramatically. The smaller the object, the faster it has to spin to conserve the same amount of angular momentum. But pulsars do not spin forever at the same rate, they slow down. Gradually, over millions of years, the rotation period lengthens. The energy required to power the beams, to accelerate the particles, to maintain the magnetic field, all of that energy comes from the rotational kinetic energy of the star itself. As the star radiates energy into space, it loses angular momentum and spins more slowly. The slowdown is tiny, typically measured in microseconds per year, but it is measurable and it is relentless. For most pulsars, the slowdown rate is remarkably steady. This steadiness is what makes pulsars useful as cosmic clocks. Once you measure a pulsar's period and its rate of slowdown, you can predict when the next pulse will arrive with extraordinary precision. The best pulsars, the ones called millisecond pulsars, are stable to within a few microseconds over timescales of years or even decades. That rivals the stability of the best atomic clocks on Earth. Millisecond pulsars are a special subclass. They spin much faster than typical pulsars, completing anywhere from a few dozen to a few hundred rotations per second. The reason they spin so fast is not that they collapsed from more massive stars, it is that they were spun back up. Most millisecond pulsars are found in binary systems orbiting a companion star. Over time, material from the companion star falls onto the neutron star, and as that material spirals inward, it transfers angular momentum to the neutron star, gradually spinning it up to millisecond periods. The process is called recycling, and it can take millions of years. The result is a pulsar that spins incredibly fast and has a very weak magnetic field compared to a young pulsar. The weak field means the pulsar loses energy more slowly, so its rotation period is more stable. Millisecond pulsars are the most precise natural clocks in the universe, and astronomers use them for everything from testing general relativity to searching for gravitational waves. Pulsar timing arrays are networks of millisecond pulsars monitored over long periods to detect tiny deviations in their pulse arrival times. If a gravitational wave passes through the space between Earth and a pulsar, it stretches and compresses spacetime, causing the pulses to arrive slightly early or slightly late. By monitoring dozens of pulsars simultaneously, astronomers can detect gravitational waves with wavelengths spanning light years, far longer than anything detectable by ground-based interferometers like LIGO. In June 2023, multiple pulsar timing array collaborations announced the detection of a low-frequency gravitational wave background, likely produced by merging supermassive black holes across the universe. But pulsars are not all the same. There are different types, and each type tells a different story about the neutron star producing it. Radio pulsars are the classic type, the ones Bell Burnell discovered. They emit pulses primarily in the radio part of the spectrum, and they are by far the most common type known. X-ray pulsars emit most of their energy in X-rays, and are usually found in binary systems where they are actively accreting material from a companion star. The infalling material heats up as it spirals inward, emitting X-rays before it reaches the surface. Some pulsars emit across the entire electromagnetic spectrum. The Crab pulsar, located in the remnant of a supernova observed by Chinese astronomers in 1054, emits pulses in radio, optical, X-ray, and gamma-ray wavelengths. It is one of the youngest known pulsars, only about 1,000 years old, and it is still spinning down from the initial high rotation rate it had after the supernova. The Crab pulsar rotates about 30 times per second, and is slowing down at a rate that makes it one of the easiest pulsars to study in detail. Gamma-ray pulsars are a more recent discovery. Before the launch of NASA's Fermi Gamma Ray Space Telescope in 2008, only a handful of pulsars were known to emit gamma rays. Fermi changed that. By scanning the entire sky every 3 hours, Fermi detected gamma-ray emission from more than 200 pulsars, many of which were not previously known as radio pulsars. Some of these gamma-ray pulsars are radio quiet, meaning they do not emit detectable radio pulses at all. This suggests that the beams produced by different pulsars can have different shapes and orientations, and in some cases the radio beam may not sweep across Earth even though the gamma-ray beam does. Then there are magnetars, neutron stars with magnetic fields 1,000 times stronger than typical pulsars. Magnetars do not behave like regular pulsars. Their magnetic fields are so intense that they produce sudden bursts of X-rays and gamma rays, sometimes releasing more energy in 1/10 of a second than the Sun emits in 100,000 years. These outbursts are thought to be caused by starquakes or by the sudden rearrangement of the magnetic field lines threading through the crust. Magnetars are rare. Only about 30 have been confirmed, compared to thousands of ordinary pulsars. The diversity among pulsars raises a question. Are all neutron stars pulsars, or are pulsars just a phase that some neutron stars go through? The answer seems to be the latter. Pulsars require two things: a strong magnetic field and fast rotation. As a neutron star ages, its magnetic field weakens and its rotation slows. Eventually, the star spins too slowly and the magnetic field is too weak to produce detectable beams. The star is still there, still a neutron star, but it is no longer a pulsar. It has become what astronomers call a dead pulsar, an object that is effectively invisible unless something happens to spin it back up, or unless it happens to be close enough to study through other means. This means that for every pulsar we can detect, there are likely dozens or hundreds of neutron stars we cannot see. The visible pulsars are the young ones, the recycled ones, and the ones whose beams happen to point toward Earth. The rest are out there, spinning quietly in the dark, waiting for a chance encounter with a passing star or a cloud of gas that might light them up again. The discovery of pulsars solved a problem that had been nagging astronomers since the 1930s. In 1932, a physicist named Lev Landau proposed that stars could collapse into objects held up by neutron degeneracy pressure. In 1934, Walter Baade and Fritz Zwicky suggested that supernovae might produce such objects, which they called neutron stars. But for decades, no one had seen one. Neutron stars were a theoretical prediction with no observational confirmation. Pulsars changed that. Within months of the discovery, theorists worked out that the only objects capable of producing such rapid, regular pulses were neutron stars. The rotation rates ruled out white dwarfs, which would fly apart if they spun that fast. Black holes could not produce the pulses because there is no surface to emit from. Neutron stars were the only option. The discovery of pulsars was not just the discovery of a new type of astronomical object. It was the confirmation that neutron stars, objects so extreme they seemed almost impossible, actually existed. Jocelyn Bell Burnell did not receive the Nobel Prize for her discovery. The 1974 Nobel Prize in Physics was awarded to Anthony Hewish and Martin Ryle. Hewish for the discovery of pulsars and Ryle for pioneering work in radio astronomy. Bell Burnell was not included. The decision remains one of the most controversial omissions in the history of the Nobel Prize. Many in the scientific community, including Bell Burnell herself in later interviews, have pointed out that she was the one who noticed the signal, insisted on following it up, and did the painstaking work of analysing the data. Hewish was her supervisor and deserves credit for creating the environment in which the discovery was made, but the exclusion of Bell Burnell has been widely criticised. Bell Burnell has spoken about it with grace. In interviews, she said that as a graduate student she was not expecting to win a Nobel Prize, and that the prize typically goes to senior scientists rather than students. She has also noted that the attention she received after being passed over has given her a platform to advocate for underrepresented groups in science, which she considers valuable in its own right. In 2018, she was awarded the Special Breakthrough Prize in Fundamental Physics and donated the entire $3 million prize to fund scholarships for women, minorities, and refugees studying physics. The story of the discovery is worth remembering because it is a reminder that science is done by people, and people make decisions about who gets credit. Bell Burnell made the observation. She did the work. And the field moved on without giving her the recognition that most historians of science now agree she deserved. But the pulsars themselves do not care about credit or prizes. They keep spinning, they keep pulsing, and they keep giving us information. Pulsar timing is now one of the most precise measurement techniques in all of astronomy. By recording the arrival times of pulses over months or years, astronomers can measure a pulsar's position in the sky to within a few milliseconds, detect the gravitational influence of unseen planets or companion stars, measure the pulsar's motion through space, and even test the predictions of general relativity in the strong field regime where the theory is hardest to test. One of the most famous tests involved a pulsar called Pulsar B1913-16, discovered in 1974 by Russell Hulse and Joseph Taylor. This pulsar is in a binary system with another neutron star, and the two objects orbit each other every 8 hours. General relativity predicts that such a system should emit gravitational waves, losing energy and gradually spiralling inward. Hulse and Taylor measured the orbit with extraordinary precision and found that the orbital period was decreasing by exactly the amount predicted by general relativity. The measurement was so precise that it provided the first indirect evidence for the existence of gravitational waves decades before LIGO detected them directly. Hulse and Taylor were awarded the Nobel Prize in 1993 for that work. Pulsars have also been used to discover planets. In 1992, Alexander Wolszczan detected periodic variations in the pulse arrival times from a millisecond pulsar called Pulsar B57-12. The variations were caused by the gravitational tug of planets orbiting the pulsar. This was the first confirmed detection of planets outside our solar system. The planets are small, likely rocky, and they orbit in the radiation-blasted environment of a pulsar, which makes them utterly inhospitable to life. But their discovery proved that planet formation can occur in the aftermath of a supernova, which was not something anyone had predicted. The precision of pulsar timing has one more application that borders on science fiction, but is entirely real. If we ever build a spacecraft capable of travelling to another star, pulsar timing could be used for navigation. The idea is simple. Just as GPS satellites use precise atomic clocks to triangulate your position on Earth, a spacecraft could use the arrival times of pulses from known pulsars to determine its position in space. The pulsars act as cosmic beacons, and because their pulse periods are so stable and so well measured, they provide a reference frame that works anywhere in the galaxy. NASA has tested this concept using X-ray detectors on the International Space Station, and the results are promising. Pulsar-based navigation could become a real tool for deep space exploration. All of this from a bit of scruff on a chart in 1967. A faint repeating signal that a graduate student noticed and decided to follow up on. That signal turned out to be a rotating neutron star, and that neutron star turned out to be one of thousands scattered across the galaxy, each one spinning in the dark, each one sending out a beam of radiation that sweeps across space with a regularity that rivals the best clocks humanity has ever built. Pulsars are loud, they are visible. They are detectable across vast distances because their beams are so focused and so bright. But not all neutron stars are pulsars. Some emit radiation in ways that do not fit the lighthouse model. Some produce steady glows instead of pulses, and some, as we are about to see, produce things that should not be there at all. Things like antimatter. Vast clouds of it, streaming away from objects that by all rights should not be capable of producing antimatter in those quantities. One of those objects is called Geminga, and it is sitting a few hundred light years away, quietly spraying positrons into space, and we have no idea why. All of this from a bit of scruff on a chart in 1967. A faint repeating signal that a graduate student noticed and decided to follow up on. That signal turned out to be a rotating neutron star, and that neutron star turned out to be one of thousands scattered across the galaxy, each one spinning in the dark, each one sending out a beam of radiation that sweeps across space with a regularity that rivals the best clocks humanity has ever built. Pulsars are loud, they are visible. They are detectable across vast distances because their beams are so focused and so bright. But not all neutron stars are pulsars. Some emit radiation in ways that do not fit the lighthouse model. Some produce steady glows instead of pulses. And some, as we're about to see, produce things that should not be there at all. Things like antimatter. Vast clouds of it, streaming away from objects that by all rights should not be capable of producing antimatter in those quantities. One of those objects is called Geminga, and it is sitting a few hundred light years away, quietly spraying positrons into space, and we have no idea why. The name Geminga is not a catalogue designation, it is a nickname, and it comes from Italian dialect. In the Milanese dialect, the phrase Geminga means it is not there. The name was given to the object in the 1980s by Giovanni Bignami and his team because Geminga was not there in radio observations. It was invisible to radio telescopes, but it was one of the brightest sources in the gamma-ray sky, glowing steadily in high-energy photons while remaining completely silent at radio wavelengths. For years, astronomers could not figure out what it was. No pulsations, no obvious optical counterpart, just a patch of sky that lit up in gamma rays and did nothing else. The mystery deepened in the early 90s when observations from the Compton Gamma Ray Observatory and later ground-based telescopes finally detected faint pulsations in the gamma ray signal. The pulsations had a period of about 0.23 seconds, roughly 4 pulses per second. That was the clue that confirmed what some had suspected. Geminga was a pulsar after all, a neutron star spinning rapidly, with a magnetic field channeling radiation into beams, but the beams did not include radio waves, or at least not in a direction we could detect. Geminga was radio quiet, a pulsar whose lighthouse beams swept past Earth only in gamma rays. The discovery of Geminga as a pulsar solved one mystery and opened another. Why was it radio quiet? Most pulsars emit across multiple wavelengths, with radio being the easiest to detect. Geminga broke the pattern. Later observations suggested that the geometry of its magnetic field might be unusual, with the radio beam pointing in a direction that misses Earth entirely, while the gamma-ray beam happens to sweep right across us. Or it could be that Geminga simply does not produce strong radio emission, a possibility that would make it part of a class of gamma-ray pulsars that were largely unknown before space-based gamma-ray telescopes came online. But the radio silence was not the strangest thing about Geminga. The strangest thing was what started showing up in cosmic ray detectors in the early 2000s. Positrons, lots of them. More than there should have been. Positrons are the antimatter counterparts of electrons. Same mass, opposite charge. When a positron meets an electron, the two annihilate each other, converting their mass entirely into energy in the form of gamma rays. Positrons are produced naturally in certain high-energy processes. Radioactive decay of some isotopes produces them. Cosmic ray collisions in interstellar space produce them, and particle accelerators on Earth produce them routinely. But in each case, positrons are rare compared to electrons. The universe is made of matter, not antimatter, and positrons do not stick around long. They find an electron, annihilate, and vanish. Cosmic rays, the high-energy particles that constantly bombard Earth from space, contain a mix of protons, electrons, heavier nuclei, and a small fraction of positrons. The ratio of positrons to electrons in cosmic rays is something physicists have been measuring for decades. The expectation, based on standard models of where cosmic rays come from and how they propagate through the galaxy, is that the positron fraction should decrease as energy increases. High-energy positrons should be rare, because the processes that produce them, mostly collisions between cosmic rays and interstellar gas, do not favour positrons at high energies. In 2008, a satellite experiment called Pamela, the payload for antimatter-matter exploration and light nuclei astrophysics, published results that did not match the expectation. Pamela measured the positron fraction in cosmic rays up to energies of about 100 gigaelectronvolts or GeV, and found that instead of decreasing with energy, the positron fraction increased. The rise started at around 10 GeV and continued upward through the entire range Pamela could measure. The excess was clear, statistically significant, and completely unexpected. This was not a small anomaly. The positron fraction at high energies was roughly double what the standard models predicted. Something was producing extra positrons, and whatever that something was, it was not accounted for in the existing framework. The announcement made headlines, not because positrons are inherently exciting, though they are, but because one of the proposed explanations for the excess was dark matter. Dark matter, the invisible substance that makes up about 85% of the matter in the universe, does not emit light and has never been directly detected. But some theoretical models predict that dark matter particles could annihilate with each other when they collide, producing ordinary particles as byproducts. Electrons and positrons are among the particles that certain dark matter models predict should be produced in these annihilations. If dark matter was annihilating in a halo around the Milky Way, and if the rate of annihilation was high enough, it could in principle produce the extra positrons Pamela was seeing. The idea was tantalizing. Dark matter had been inferred from its gravitational effects for decades, but no one had ever seen a direct signal from it. The positron excess, if it was really caused by dark matter, would be the first direct evidence that dark matter particles interact with each other and produce detectable byproducts. The dark matter interpretation faced problems almost immediately. For one thing, the energy spectrum of the positron excess did not quite match what most dark matter models predicted. For another, the annihilation rate required to produce the observed excess was higher than what many models allowed. And there was a third problem, one that became clearer as more data came in. There were other sources of high-energy positrons that had not been fully accounted for. Astrophysical sources. Nearby astrophysical sources, specifically pulsars. Pulsars are particle accelerators. The intense magnetic fields near a spinning neutron star can accelerate electrons and positrons to enormous energies. Those particles spiral along the magnetic field lines, emit radiation, and eventually escape into space. If a pulsar is close enough and energetic enough, the positrons it produces could reach Earth and show up in cosmic ray detectors as an excess above the background. Geminga, it turns out, is both close and energetic. It sits roughly 250 to 300 parsecs away, which is about 800 to 1000 light-years. That is close by galactic standards. Most pulsars are thousands of light-years away, too far for their positrons to contribute significantly to the local cosmic ray flux. But Geminga is in the neighbourhood, and it is not just any pulsar. It is one of the brightest gamma-ray sources in the sky, which means it is dumping enormous amounts of energy into its surroundings. The connection between Geminga and the positron excess was not obvious at first. Pulsars had been considered as possible sources before Pamela, but the calculations suggested they could not produce enough positrons to explain the excess. The problem was diffusion. Positrons do not travel in straight lines through space. They scatter off magnetic fields in the interstellar medium, bouncing around in a kind of random walk. The more scattering they do, the longer it takes them to reach Earth, and the more their energy gets spread out. Standard models of cosmic ray diffusion predicted that even a nearby pulsar like Geminga would not be able to deliver enough high-energy positrons to Earth to account for the Pamela results. Then, in 2017, observations from the High-Altitude Water Cherenkov Observatory, or HAWC, located in Mexico, detected something unusual around Geminga. HAWC is a gamma-ray telescope that detects very high-energy gamma rays in the tera-electron-volt range, or TeV. 1 TeV is 1000 GeV, 1,000 times more energetic than the positrons Pamela was measuring. Hawke found extended gamma-ray emission around Geminga, a kind of glowing halo of gamma rays that stretched for dozens of light-years around the pulsar. That halo was a clue. Gamma rays at TeV energies are produced when high-energy electrons and positrons collide with low-energy photons in space, boosting them up to TeV energies through a process called inverse Compton scattering. The presence of the gamma-ray halo meant that there were high-energy electrons and positrons surrounding Geminga, trapped in the region around the pulsar by the local magnetic fields. Those particles were the fuel for the gamma-ray glow, and if they were there, in large numbers, then Geminga was producing them. The Hawke team ran the numbers. If Geminga was surrounded by a halo of high-energy particles, and if those particles were diffusing outwards slowly, then Geminga could in fact be contributing a significant fraction of the positron excess detected by Pamela. Some of the early estimates suggested that Geminga alone could account for most of the excess at energies around 1 TeV. Other analyses were more conservative, suggesting that Geminga contributed a large share but not all of it. The key uncertainty was diffusion. How fast do positrons escape from the region around Geminga and propagate through the galaxy? If diffusion is slow, then the positrons stay trapped near the pulsar for a long time, and only a small fraction ever reach Earth. If diffusion is faster, then more positrons escape and the contribution to the cosmic ray flux at Earth is larger. Different studies used different assumptions about the local diffusion rate, and they got different answers. A 2022 analysis posted on NANOGrav argued that Geminga could explain the positron excess if the pulsar was converting about 30% of its rotational energy into accelerating electrons and positrons, but only if the diffusion coefficient near Geminga was higher than the average galactic value. If diffusion was slow, then Geminga's contribution dropped, and other sources would be needed to explain the rest of the excess. Another study, also from HAWC data, concluded that pulsars in general, not just Geminga, provide the dominant contribution to the positron excess. The study identified 2 nearby pulsars, Geminga and another called PSR B06456 plus 14, as the primary candidates. Together, they could account for a large fraction of the observed positrons without requiring dark matter annihilation at all. The implication was clear. The positron excess, which had been touted as possible evidence for dark matter, could be explained by ordinary astrophysical sources. Nearby pulsars, doing what pulsars do, accelerating particles and injecting them into the local cosmic ray population. No new physics required, no dark matter annihilation, just neutron stars. This was both a relief and a disappointment. A relief because it meant the standard model of astrophysics was not broken. Pulsars were already known to be particle accelerators. The positron excess was surprising, but it fit within the framework of known processes once the contribution from nearby sources was properly accounted for. A disappointment because it meant the positron excess was probably not a dark matter signal. The first potential direct detection of dark matter had turned into a lesson about making sure you understand all the conventional sources before jumping to exotic explanations, but calling it settled would be premature, because the debate over Geminga's contribution is still ongoing. Different teams, using different methods and different assumptions, continue to get different answers. Some argue that Geminga is the main source, others say it contributes, but not enough to explain the entire excess, and a few suggest that even with Geminga included, there is still room for a dark matter component. The problem is that we do not have a perfect model of how cosmic rays diffuse through space. Diffusion depends on the strength and structure of the magnetic field, which varies from place to place in the galaxy. Near a pulsar, the magnetic field might be stronger or more tangled than average, which would slow diffusion. Farther out in the general interstellar medium, diffusion might be faster. We have measurements of the average diffusion rate across the galaxy, but local variations can be large, and those variations directly affect how many positrons from a given source reach Earth. The gamma-ray halo around Geminga gives us a snapshot of the particle population near the pulsar, but translating that into a prediction for the cosmic ray flux at Earth requires modelling the diffusion process over hundreds of light years. Small changes in the assumed diffusion coefficient can double or halve the predicted positron flux, which means the answer depends heavily on assumptions that are hard to test directly. There is another complication. Geminga is not the only pulsar in the neighbourhood. There are others, some of which are also likely producing positrons. If you add up the contributions from multiple nearby pulsars, the total positron flux increases, and the need for any additional sources, whether dark matter or something else, decreases. But measuring the contribution from each individual pulsar is difficult because we do not know their exact ages, their particle injection rates, or the details of how their positrons propagate through space. What we do know is that Geminga is unusual. It is close. It is energetic. It has a gamma-ray halo that provides direct evidence of a surrounding population of high-energy particles. And it is radio quiet, which means it was overlooked for years in surveys that focused on radio pulsars. If Geminga had been a normal radio pulsar, it would have been discovered much earlier, and its role in the positron excess might have been recognised sooner. The fact that Geminga is radio quiet also raises a question. How many other Geminga-like pulsars are out there, undetected because they do not emit radio pulses? Gamma-ray surveys with satellites like Fermi have found hundreds of gamma-ray pulsars, many of which are radio quiet or radio faint. If even a fraction of those are nearby and energetic, they could be contributing to the cosmic ray population in ways that have not been fully accounted for. The positron excess is not the only anomaly in cosmic rays. There are others: an excess of antiprotons at certain energies, an unexpected break in the electron spectrum, features in the energy distribution of heavier nuclei that do not quite match the models. Each of these anomalies could be a sign of new physics, or it could be a sign that the models of cosmic ray sources and propagation are incomplete. The positron excess, once the most prominent of these anomalies, has shifted from being a dark matter candidate to being a test case for how well we understand pulsar contributions to cosmic rays. One of the reasons the positron excess generated so much excitement is that dark matter remains one of the biggest unsolved problems in physics. We know it is there. We can see its gravitational effects in the rotation curves of galaxies, in the motion of galaxy clusters, in the patterns of the cosmic microwave background, and in the large-scale structure of the universe. But we do not know what it is made of. Decades of direct detection experiments have failed to find dark matter particles. Decades of particle collider experiments have failed to produce them. The positron excess offered a glimmer of hope that dark matter might be revealing itself indirectly, through the particles produced when dark matter particles collide and annihilate. That hope has dimmed, but it has not gone out entirely. Some models of dark matter still predict positron excesses of the right magnitude and energy range. And while pulsars can explain much of the observed excess, they do not necessarily explain all of it. There is still room, in the data, for a small contribution from something else. Whether that something else is dark matter or another astrophysical source we have not identified yet remains an open question. Geminga itself is not done surprising us. In addition to the gamma-ray halo, observations have also detected extended X-ray emission around the pulsar. The X-rays are thought to come from synchrotron radiation, the same process that produces radio waves in other pulsars. The fact that Geminga emits X-rays but not detectable radio waves suggests that the particle acceleration mechanism near the pulsar is selective, favouring higher energy photons. Why that is the case is still unclear. The age of Geminga is estimated to be around 300,000 years, making it a relatively young pulsar by astronomical standards. Young pulsars are more energetic because they are still spinning down from their initial high rotation rates. As a pulsar ages, it loses rotational energy, and the particle acceleration becomes less efficient. In a few million years, Geminga will have slowed down enough that it will no longer be a significant source of high-energy positrons. But right now, it is in its prime, spinning 4 times per second and pouring energy into its surroundings. The positron shower from Geminga is not something you can see or feel. The positrons are not arriving in a beam pointed at Earth. They are diffusing through space, scattering off magnetic fields and arriving at Earth from all directions. the flux is tiny. A single positron detector on a satellite might register a few extra positrons per hour compared to what the background models predict. But that small excess, multiplied across all energies and all directions, adds up to a signal that required years of careful measurement to detect. And it is a signal that matters, because every positron that hits a detector is a piece of evidence about where it came from, how it travelled, and what processes produced it. The positron excess is not just a puzzle about antimatter. It is a puzzle about neutron stars, about magnetic fields, about particle acceleration, and about how the galaxy is wired together at the level of individual particles travelling for hundreds of years through space. Geminga is roughly 800 light-years away. A positron produced by Geminga today will not reach Earth for another 800 years, assuming it travels in a straight line, which it does not. The actual travel time, accounting for diffusion, is much longer, possibly tens of thousands of years. The positrons we are detecting now were produced by Geminga tens of thousands of years ago, when the pulsar was even younger and even more energetic than it is today. Think about that for a moment. We are measuring particles that left their source before human civilization existed. Before agriculture, before writing, before the first cities, those particles have been wandering through space, bouncing off magnetic field lines, losing energy, changing direction for longer than recorded history. And they are arriving now at detectors orbiting Earth, carrying information about a neutron star that has been spinning in the dark for 300,000 years. The story of the positron excess is a reminder that the universe is not static. It is full of processes that happen on timescales much longer than a human life. Geminga has been producing positrons for millennia, and it will continue producing them for millennia more. The cosmic ray flux we measure today is the cumulative result of contributions from pulsars, supernova remnants, and other sources scattered across the galaxy, each one injecting particles into the interstellar medium over thousands or millions of years. The positrons are not new, they have always been there. We just did not notice them until our detectors became sensitive enough. The positron excess is not the only mystery associated with neutron stars, it is not even the strangest. But it is one of the clearest examples of how neutron stars can produce effects that reach across interstellar distances and show up in measurements made in our own solar system. Geminga is not special because it is unique. It is special because it is close enough that we can study it in detail. There are probably dozens or hundreds of other neutron stars doing the same thing, accelerating particles and injecting them into the galaxy. We just cannot see them because they are too far away, or because their beams do not point toward us. The fact that we can detect the positron excess at all is a testament to how sensitive modern particle detectors have become. Pamela, launched in 2006, was designed to measure the composition of cosmic rays with high precision. It operated for years, collecting data from an orbit a few hundred kilometers above Earth's surface. The Fermi Gamma Ray Space Telescope, launched in 2008, has been mapping the gamma-ray sky continuously for more than a decade. HALCY, the ground-based gamma-ray observatory, uses a different technique, detecting the showers of particles produced when high-energy gamma rays hit Earth's atmosphere. Each of these instruments contributes a piece of the picture, and together they have turned the positron excess from a vague hint into a well-measured phenomenon that demands an explanation. The explanation is still being worked out. Pulsars are the leading candidates. Geminga is one of the leading pulsars, but the details matter, and the details are hard to pin down. How much of the excess comes from Geminga versus other pulsars? How much comes from pulsars versus other sources like supernova remnants? Is there any contribution from dark matter, or has that possibility been ruled out? These are questions that require more data, better models, and a deeper understanding of how particles propagate through the galaxy. What we can say with confidence is that neutron stars are not just dense remnants of dead stars. They are active participants in the ecology of the galaxy. They produce particles, they emit radiation, and they shape the environment around them in ways that can be detected across hundreds of light years. Geminga, spinning quietly in the constellation Gemini, invisible to the naked eye, undetectable in radio, is one of the brightest objects in the gamma-ray sky, and a major contributor to the antimatter flux reaching Earth. It is doing all of this without fanfare, without pulsing in a way that makes it easy to spot, just sitting there, accelerating particles and pouring them into space. And Geminga is not alone. there are other neutron stars producing signals that do not fit the standard pulsar model. Signals that last too long, repeat too regularly, or come from objects that should not be active at all. Some of those signals challenge our understanding even more than the positron excess does. One of them is coming from an object with the designation GPM J1839-10, and it is doing something that by all rights should be impossible. It is pulsing every 22 minutes, not every second, not every millisecond, every 22 minutes, for an object that should have stopped pulsing millions of years ago, and nobody can explain it. The object was found in 2022 by astronomers working with the Murchison Wide Field Array, a radio telescope in Western Australia. The array is designed to scan large sections of the sky at once, looking for transient events, things that appear and disappear, things that flicker or pulse or do anything other than sit there glowing steadily. The telescope monitors the radio sky at low frequencies, the kind of frequencies where pulsars and other exotic objects tend to be brightest, and in the data from one of those scans, buried in the noise, the team found a signal that repeated like clockwork. One pulse every 22 minutes, or to be more precise, every 1,318.1957 seconds. 22 minutes is just easier to say. The signal was not a single blip, it was a series of radio bursts, each one lasting up to about 5 minutes. So the pattern was roughly this: silence for 17 minutes, then a burst of radio emission that ramped up, peaked, and faded over the course of 5 minutes, then silence again for another 17 minutes, then another burst. Over and over, with a regularity that was unsettling in its precision. The team published their findings in the journal Nature in July 2023. By that time, they had already gone back through archival radio data to see if the object had been active before. It had. The signal showed up in observations going back to 1988. That meant the object had been pulsing, in this same pattern, for at least 33 years, and likely much longer. The archives only went back so far. For all we know, it has been pulsing since before humans invented radio telescopes. The location of the object is about 15,000 light-years away, somewhere in the Scutum constellation. That places it well within the Milky Way, not in some distant galaxy. It is a local object, cosmically speaking, close enough that we should be able to study it in detail, far enough that we cannot resolve it into anything more than a point of light in our detectors. We know where it is, we know what it is doing, we do not know what it is. Here is the problem. A 22-minute repetition period is too slow for a pulsar, too slow for a magnetar, too slow for any known type of neutron star to sustain the kind of emission we are detecting. Let me explain why. Pulsars, as we have established, are spinning neutron stars. The pulses we detect are caused by beams of radiation sweeping across our line of sight as the star rotates. The pulse period is the rotation period. A pulsar that pulses once per second is rotating once per second. A millisecond pulsar that pulses hundreds of times per second is rotating hundreds of times per second. The energy to produce the beams comes from the rotational kinetic energy of the neutron star. As the star emits radiation, it loses energy and slows down. The rotation period gradually lengthens over time. For a pulsar to produce detectable radio emission, it needs two things: a strong magnetic field and a fast rotation. The magnetic field channels the charged particles that produce the radiation. The fast rotation keeps those particles moving at relativistic speeds, which is what generates the synchrotron radiation we detect as radio waves. If the rotation is too slow, the particles do not accelerate enough, and the emission drops below detectable levels. The pulsar effectively turns off. It becomes a dead pulsar, still a neutron star, still spinning, but no longer emitting beams. The cutoff for when a pulsar dies, the point where the rotation becomes too slow to sustain emission, is not a sharp line. It depends on the strength of the magnetic field and the details of the magnetosphere. But as a rough rule of thumb, pulsars with periods longer than about 10 to 20 seconds are not expected to emit detectable radio waves. They have crossed what is sometimes called the pulsar death line. Their rotation is too slow. The magnetic field can no longer do the work required to accelerate particles to the energies needed for emission. GPM J1839-10 has a period of 22 minutes. That is more than 60 times longer than the typical death line. It should not be emitting anything. And yet it is. Loud and clear. Every 22 minutes. For at least 33 years and counting. Magnetars are a possible loophole. Magnetars, as mentioned earlier, are neutron stars with magnetic fields about 1,000 times stronger than typical pulsars. The extreme magnetic field gives them access to energy reserves that ordinary pulsars do not have. Magnetars can produce bursts of X-rays and gamma rays even when their rotation is relatively slow. Some magnetars have periods of a few seconds, much longer than typical pulsars but still short compared to 22 minutes. The magnetic field does the heavy lifting, providing energy through magnetic reconnection and other processes that do not rely solely on rotation. Could GPM J1839-10 be a magnetar? That is the leading theory. If it is, it would be what astronomers are calling an ultra-long period magnetar. A neutron star with a magnetic field strong enough to sustain emission, despite a rotation period that is absurdly slow by neutron star standards. The idea is not completely out of left field. Magnetars are known to be strange. Some of them produce quasi-periodic oscillations, repeating patterns of emission that do not fit the standard pulsar lighthouse model. Some emit in bursts that seem to be triggered by starquakes or magnetic field rearrangements. An ultra-long period magnetar would be an extreme version of something that is already known to be extreme. But there are problems with the magnetar explanation. For one thing, most magnetars are young. They have strong magnetic fields because they were born that way, and magnetic fields decay over time. An old magnetar, one that has had millions or tens of millions of years to cool down and lose magnetic field strength, should not be as active as GPM J1839-10 appears to be. Yet the slow rotation period suggests this object is old. Neutron stars spin down over time. A 22-minute period means this object has been spinning down for a very long time, possibly hundreds of millions of years or more. How does an object stay active for that long if its magnetic field is supposed to be decaying? One possibility is that the magnetic field is not decaying as fast as expected. Some theoretical models suggest that certain configurations of magnetic fields inside a neutron star, particularly those threaded through a superconducting core, could be much more stable over time. If that is the case, a magnetar could maintain a strong field for much longer than standard models predict, allowing it to remain active even as its rotation slows to a crawl. Another possibility is that GPM J1839-10 is not a neutron star at all. Some researchers have explored the idea that it could be a white dwarf, a different kind of stellar remnant. White dwarfs are the cores of stars that were not massive enough to explode as supernovae. They are dense, but not nearly as dense as neutron stars. A typical white dwarf has the mass of the Sun packed into an object about the size of Earth. White dwarfs do not usually emit radio pulses, but under certain conditions, particularly in binary systems where a white dwarf is accreting material from a companion star, strange things can happen. The accretion can spin the white dwarf up, strengthen its magnetic field, and potentially produce emission that looks pulse-like. The white dwarf hypothesis has some appeal because white dwarfs can rotate more slowly than neutron stars without falling apart. A white dwarf could in principle sustain a 22-minute rotation period without violating any fundamental physical limits. But the white dwarf model struggles to explain the observed emission. White dwarfs do not typically produce the kind of coherent, periodic radio bursts that GPM J1839-10 emits. The emission pattern looks more like what you would expect from a neutron star, specifically a magnetar, than from a white dwarf, and the location of the object, 15,000 light-years away in the galactic plane, is more consistent with a neutron star population than with a white dwarf population. So we are left with an ultra-long period magnetar as the best available explanation, even though that explanation requires pushing the boundaries of what we think magnetars can do. It is not a satisfying answer. It is more of a placeholder, a label that describes what we're seeing without fully explaining how it works. The emission itself is strange. Each burst lasts up to 5 minutes, which is long for a pulsar pulse. Most pulsar pulses are milliseconds, or at most a few seconds. A 5-minute pulse suggests that the emission region, the part of the magnetosphere where the radio waves are generated, is large, and that the process producing the emission is sustained rather than impulsive. The pulses are not all identical, some are brighter than others. Some show structure, with peaks and valleys in the intensity, and the polarization of the radio waves, the direction in which the electromagnetic field oscillates, changes during the pulse in ways that suggest a complex magnetic field geometry. Later studies of the object, conducted after the initial discovery, found unusual polarization features that strengthened the Magnetar interpretation. Polarization is a property of light that describes the orientation of the electromagnetic field. Radio waves from pulsars are often highly polarized, and the polarization can change as the beam sweeps across the line of sight. The polarization patterns from GPM J1839-10 are consistent with emission from a magnetosphere dominated by a strong complex magnetic field, the kind of field you would expect from a magnetar. There is also evidence that the object might be related to other mysterious phenomena. Fast radio bursts, or FRBs, are brief, intense pulses of radio emission that last only milliseconds but release as much energy as the sun emits in days or weeks. The origin of FRBs is still debated, but magnetars have emerged as one of the leading candidates. If GPM J1839-10 is a magnetar, and if it is producing long-period radio bursts, it could represent a link between magnetars, long-period transients, and FRBs. That link is speculative at this point, but it is one of the reasons the discovery has generated so much interest. The fact that the object was hiding in archival data for decades is both embarrassing and enlightening. Embarrassing because it means astronomers had been looking at the signal for years without recognizing it. Enlightening because it shows how easy it is to miss things when you do not know what to look for. The original surveys that captured the data were not designed to search for signals with periods as long as 22 minutes. They were looking for pulsars with periods of seconds or milliseconds. A 22-minute signal, spread across multiple observations, would not have triggered any of the automated detection algorithms. It just looked like noise. The discovery of GPM J1839-10 has triggered a hunt through radio archives around the world. If one ultra-long period object exists, there are probably others. Astronomers are now going back through decades of data, searching for similar signals that might have been overlooked. The hope is to find more examples and to start building a picture of what this class of objects looks like. Are they all magnetars? Are they all in the same part of the galaxy? Do they all have similar emission patterns? Or is GPM J1839-10 a one-off, a freak occurrence that does not fit into any broader category? The search has already turned up a few candidates, objects with long periods and unusual emission properties that might belong to the same class. None of them are as well studied as GPM J1839-10, and none have been confirmed beyond doubt. But the fact that candidates exist suggests this is not a singleton. There is a population out there, waiting to be characterized. One of the researchers involved in the discovery, Dr. Simona Giacintucci, a research astronomer at the Naval Research Laboratory, put it this way: "This enigmatic object has been hiding in the data for decades. We just did not know we had to look for it until its discovery by the Murchison Wide Field Array." That quote captures the essence of the problem. GPM J1839-10 is not new. It has been doing its thing for at least 33 years, possibly much longer. We just were not paying attention. Another researcher, Dr. Tracy Clark, also at the Naval Research Laboratory and project scientist for an instrument called VLEET that contributed to the follow-up observations, said this: "Current understanding says this object should not emit radio waves, and yet we are detecting them across several decades and we are not sure why. That is an exciting mystery. The phrasing is careful, not sure why. That is the scientific way of saying we have no idea. The mystery deepens when you consider the implications for neutron star physics. If GPM J1839-10 is a magnetar, and if magnetars can remain active with rotation periods as long as 22 minutes, then the models of how magnetars work need to be revised. The standard picture is that magnetars are young, fast-spinning objects with magnetic fields generated during the violent collapse that created them. Those fields decay over time, and the magnetar eventually becomes a dormant neutron star. But if GPM J1839-10 is old, and if its magnetic field is still strong enough to produce emission, then something about that standard picture is wrong. One possibility is that the magnetic field is not generated during the collapse, but is maintained by dynamo processes in the interior. A dynamo is a mechanism that converts kinetic energy into magnetic energy. Earth's magnetic field is thought to be maintained by a dynamo in the molten iron core. Some models suggest that neutron stars could have similar dynamos, powered by convection or by the differential rotation of layers within the star. If a neutron star dynamo can operate over timescales of hundreds of millions of years, It could explain how an old object like GPM J1839-10 remains magnetically active. Another possibility is that the object experienced a late-stage spin-up event. Neutron stars in binary systems can accrete material from a companion star, and that accretion can transfer angular momentum to the neutron star spinning it up. This is how millisecond pulsars are created. But GPM J1839-10 is not spinning fast. If it was spun up, it has since spun back down to a very slow rotation rate, which raises the question of how long ago the spin-up occurred and whether the current activity is a delayed consequence of that event. A third possibility is that the object is not a magnetar in the traditional sense, but something else entirely. A hybrid object, a strange star, a quark star. Something that looks like a neutron star but has internal physics that differ in subtle or not so subtle ways. This is speculative territory, the kind of idea that gets floated in the discussion section of a paper, but not taken too seriously unless other evidence supports it. But the fact that such ideas are being discussed at all shows how far outside the box GPM J1839-10 is pushing the field. The 22-minute period is not just unusual, it is forbidden. That is the word astronomers keep using, forbidden. The object should not exist, at least not according to the equations that have successfully described pulsars and magnetars for the past 50 years. Those equations say that rotation and magnetic field strength are coupled. Slow rotation means weak emission. Strong emission requires fast rotation or an absurdly strong magnetic field. GPM J1839-10 has slow rotation and strong emission, which means either it has an absurdly strong magnetic field that has somehow remained intact over an immense span of time, or the equations are missing something. The missing piece could be the structure of the magnetosphere. The magnetosphere is the region around the neutron star where the magnetic field dominates the behavior of particles. In a typical pulsar, the magnetosphere is relatively simple, with field lines that extend from the magnetic poles and loop back to the star. In a magnetar, the field is stronger, and the magnetosphere is more complex, with regions where the field lines twist and reconnect, releasing bursts of energy. If GPM J1839-10 has a highly twisted, tangled magnetosphere, it could sustain emission through processes that do not fit the standard pulsar model. The twisting and untwisting of field lines could release energy in bursts, producing the periodic emission we observe without requiring the star to spin rapidly. This idea has precedent. Some magnetars produce quasi-periodic oscillations, patterns of emission that repeat on timescales of seconds to minutes. Those oscillations are thought to be caused by waves propagating through the magnetosphere, or by oscillations of the neutron star crust triggered by magnetic stresses. If GPM J1839-10 is producing a similar kind of oscillation, just on a much longer timescale, it could explain the 22-minute period without requiring the star itself to be spinning that slowly. The star could be spinning faster, say once per second or once every few seconds, and the 22-minute period could be the oscillation period of some structure in the magnetosphere. This interpretation has not been fully developed yet. It is one of several ideas being explored in the wake of the discovery. The challenge is to build a model that produces the observed emission pattern and also matches the other properties of the object, such as its brightness, its spectral characteristics, and its long-term stability. Models are easy to propose. Making them work quantitatively is harder. The hunt for similar objects is critical. One object is an anomaly. A handful of objects is a pattern. If astronomers can find 10 or 20 more ultra-long period emitters, they can start to build a statistical picture. What is the typical period? What is the range of brightnesses? Are they all radio emitters, or do some show up in X-rays or other wavelengths? Are they clustered in certain parts of the galaxy, or are they distributed randomly? Each additional object adds a data point, and data points are what turn speculation into science. The discovery of GPM J1839-10 is a reminder that the universe does not care about our models. The equations we use to describe neutron stars are approximations built on observations of the objects we have been able to detect and study. Those objects are biased toward the young, the bright, and the fast spinning. The slow, the dim, and the unusual are harder to find, and until recently we did not have the tools to search for them systematically. The Murchison Wide Field Array, with its ability to scan large areas of the sky at low radio frequencies, is one of those tools, and it is finding things that were not supposed to be there. The object is also a reminder of how much we still do not know about the life cycles of neutron stars. We understand the birth reasonably well. A massive star collapses, a neutron star forms, it starts spinning rapidly and emitting beams. We understand the middle age reasonably well. The neutron star slows down, the beams weaken, and eventually it becomes undetectable. But the details of that transition, the physics of what happens in the long, slow decline from active pulsar to dead remnant, are still murky. GPM J1839-10 is sitting somewhere in that murky region, doing something we did not predict and cannot yet explain. The long-term stability of the signal is also striking. 33 years is a long time by human standards, but it is a blink of an eye compared to the age of a neutron star. If the object has been pulsing steadily for 33 years, it has probably been pulsing for thousands or millions of years before that, which means whatever mechanism is driving the emission is robust. It is not a temporary phase, it is not a fluke. It is a stable configuration that the object has settled into, and it shows no signs of stopping. There is something unsettling about that steadiness. A 22-minute pulse, repeating without variation, for decades or longer, coming from an object 15,000 light-years away. It is the kind of signal that, if it had been discovered in the 1960s, might have briefly been labelled LGM, Little Green Men, before astronomers figured out what it really was. But we know now that nature produces clockwork. Pulsars taught us that. GPM J1839-10 is teaching us that the clockwork can run on timescales we did not expect. The object is not sending us a message, it is not a beacon. It is not trying to communicate. It is a dead star, or at least a dying star, going through the motions of some physical process that we do not yet understand. The 22-minute period is not for our benefit. It is just how the machine runs, and the fact that we can detect it, measure it, and puzzle over it is a testament to how far human technology has come. 100 years ago, we did not know neutron stars existed. 50 years ago, we had just discovered pulsars. Today, we are finding objects that break the rules we thought applied to pulsars, and we are doing it by sifting through decades of archived data that no one thought to look at closely until now. GPM J1839-10 is one object. It is a puzzle, it is a challenge, and it is almost certainly not alone. There are probably others like it scattered across the galaxy, pulsing on their own timescales, waiting for someone to point a telescope in the right direction and notice the pattern. Each one will add to the picture, each one will help refine the models, and each one will remind us that the universe is bigger, stranger, and more varied than any single theory can capture. The next step is to keep watching. GPM J1839-10 is not going anywhere. It will keep pulsing every 22 minutes for as long as whatever powers it continues to operate. Astronomers will keep monitoring it, measuring the slight variations in the pulse arrival times, looking for any changes that might hint at what is happening inside. They will search for similar objects, they will build models and test them against the data, and eventually someone will figure it out. The mechanism will be identified, the physics will be worked out, and GPM J1839-10 will go from being an impossible object to being a well-understood example of some previously unknown phase of neutron star evolution. But that day is not today. Today, GPM J1839-10 remains a mystery, a slow, steady, impossible radio pulse from a dead star that refuses to stay dead. And as we will see in the next chapter, neutron stars have other ways of making their presence known, ways that do not involve light or radio waves or any form of electromagnetic radiation, ways that involve the fabric of spacetime itself. Because when neutron stars collide, they do not just explode, they ring, and the sound they make can be heard across the universe. In 1916, Albert Einstein published a paper that predicted something so strange, so far beyond the reach of any conceivable measurement, that even he was not sure it mattered. He had just finished developing his general theory of relativity, the idea that gravity is not a force in the Newtonian sense but a curvature of space-time, caused by the presence of mass and energy. Massive objects like stars and planets warp the fabric of space around them, and other objects moving through that space follow the curves. Orbits are not the result of invisible pulling. They are objects following the straightest possible paths through curved space-time. One consequence of this framework, buried in the mathematics, was that accelerating masses should produce ripples in spacetime, gravitational waves, disturbances that propagate outward at the speed of light, stretching and compressing space itself as they pass. Einstein derived the equations that described these waves, published them, and then spent years second-guessing whether they were real or just mathematical artifacts. In later papers, he argued that they might not exist after all. Then he changed his mind again. The waves were real, he decided, but they would be so faint that no instrument would ever detect them. The universe would have to conspire to produce an event violent enough and close enough for the waves to be measurable, and even then the effect would be tiny, unimaginably tiny. Einstein was right about the waves. He was wrong about whether we could detect them. It just took a century and the collision of two neutron stars to prove it. Gravitational waves are not like other waves. They are not vibrations travelling through a medium the way sound travels through air, or ripples travel across water. They are distortions in the geometry of space and time themselves. When a gravitational wave passes through a region of space, distances change, not because objects are moving, but because the space between them is stretching and shrinking. If you and I were standing a meter apart and a gravitational wave passed between us, the distance would oscillate. First slightly more than a meter, then slightly less, then back to normal. We would not feel it. The change would be far too small. But if we had a sensitive enough measuring device, we could detect it. The challenge is that the change is absurdly small. A strong gravitational wave passing through Earth might change the distance between 2 points separated by a kilometre by an amount smaller than the width of a proton. That is the scale we're talking about, 1 part in 10 to the 21. Measuring something that's small requires an instrument so precise that it borders on the impossible. For most of the 20th century it was impossible. Physicists knew gravitational waves should exist, but building a detector sensitive enough to find them was beyond the reach of available technology. That changed in the 1960s and 70s, when physicists began designing interferometers specifically for gravitational wave detection. An interferometer works by splitting a beam of light into 2 perpendicular paths, bouncing each beam off a mirror at the end of a long arm, and then recombining the beams. If the lengths of the 2 arms are exactly the same, the light waves arrive back at the detector in phase and they interfere constructively, producing a bright signal. If the lengths are even slightly different, the waves arrive out of phase and the interference pattern changes. A gravitational wave passing through the detector would stretch one arm and compress the other, changing the interference pattern in a measurable way. The idea was elegant, the execution was brutal. Building an interferometer sensitive enough to detect gravitational waves required arms several kilometers long, mirrors polished to near-perfect smoothness, lasers stable to within a fraction of a wavelength, and vibration isolation so effective that the detector could distinguish a gravitational wave from the rumble of a passing truck, or the thermal expansion of the mirrors due to sunlight. Every source of noise had to be identified and suppressed. The project took decades. The Laser Interferometer Gravitational Wave Observatory, LIGO, consists of 2 detectors. One is located in Hanford, Washington. The other is in Livingston, Louisiana. Each detector has 2 arms, each arm 4 kilometers long, arranged in an L shape. The arms are evacuated tubes, nearly perfect vacuums with mirrors suspended at each end. A laser beam travels up and down each arm hundreds of times before recombining at the detector. The system is so sensitive that it can measure changes in the arm length smaller than 1/10,000th the diameter of a proton. LIGO began operations in the early 2000s but did not detect anything. The sensitivity was not yet high enough. The detectors were upgraded over several years, and in September 2015 they were turned back on in what was called Advanced LIGO mode. The sensitivity had been increased by a factor of 10. The detectors could now see gravitational waves from merging black holes and neutron stars out to distances of hundreds of millions of light years. On September 14th, 2015, 4 days after the detectors came back online, both LIGO sites registered a signal. The signal lasted less than a second. It started at a low frequency, about 35 Hz, and swept upward to about 250 Hz before cutting off. The pattern was unmistakable. It was the gravitational wave signature of 2 black holes spiraling into each other and merging. The black holes were each about 30 times the mass of the Sun, and they were located more than 1 billion light-years away. The collision released more energy in a fraction of a second than all the stars in the observable universe emit in the same time. Most of that energy went into gravitational waves. The detection was announced in February 2016 and made headlines around the world. It was the first direct detection of gravitational waves, confirming a prediction Einstein had made 100 years earlier. It was also the first direct observation of a binary black hole system, something that had been theorized but never seen. The scientists who led the design and construction of LIGO, Rainer Weiss, Barry Barish and Kip Thorne, were awarded the Nobel Prize in Physics in 2017. But black holes, as interesting as they are, do not produce much in the way of electromagnetic radiation when they merge. The collision happens in a vacuum. There is no matter falling in, no accretion disk, no jets. Just two event horizons smashing together and forming a larger event horizon. The gravitational waves are loud, but the event is otherwise dark. You cannot see it with a telescope. You cannot detect it with X-ray detectors or radio dishes. All you get is the space-time ripple. Neutron stars are different. Neutron stars have surfaces. They have magnetic fields. They are surrounded by matter, gas and debris from the supernova that created them. When two neutron stars spiral into each other and collide, the result is not just a gravitational wave signal, it is a full-spectrum fireworks display. Gravitational waves, gamma rays, X-rays, visible light, infrared, radio. The whole electromagnetic spectrum lights up. And astronomers had been waiting decades for the chance to observe such an event. On August 17, 2017, at 12:41 4 UTC, both LIGO detectors picked up a signal. It was different from the black hole mergers they had been detecting for the previous 2 years. The signal was quieter, lower in frequency, and it lasted much longer, about 100 seconds. Black hole mergers typically produce signals that last less than a second, because black holes are so massive that the final inspiral happens very quickly. Neutron stars are lighter, about 1 to 2 solar masses each, so they orbit each other many times before merging. The inspiral is slower, and the gravitational wave signal lasts longer. The signal was analysed in real time by automated pipelines running at the LIGO and Virgo facilities. Virgo is a gravitational wave detector in Italy, similar to LIGO but with 3-kilometre arms instead of 4. Virgo had recently joined the network and was part of the observation run when the signal arrived. Within minutes, the analysis software determined that the signal was consistent with the merger of two neutron stars. The location was narrowed down to a patch of sky roughly 30 square degrees, somewhere in the southern hemisphere. Within seconds, an automated alert was sent to astronomers around the world. This was what the multi-messenger astronomy community had been preparing for. If the collision produced electromagnetic radiation, telescopes needed to start looking immediately. Gamma-ray bursts, the explosive jets of radiation sometimes produced in neutron star mergers, fade quickly. If you want to catch one, you have to be fast. 11 seconds after the gravitational wave signal, the Fermi Gamma Ray Space Telescope detected a short burst of gamma rays coming from the same region of sky. The burst lasted about 2 seconds. That was the confirmation. The neutron stars had merged, and the collision had produced a gamma ray burst, exactly as some theoretical models had predicted. But not all models agreed on whether neutron star mergers should produce gamma ray bursts, so this was also a test of competing theories. The observation settled the debate. Neutron star mergers can produce short gamma-ray bursts. Not all of them do, but some do, and this was one of them. Telescopes began swinging toward the location. Ground-based optical telescopes in Chile scanned the region, looking for any new source of visible light. Infrared telescopes joined in. X-ray satellites repositioned themselves. Radio dishes pointed at the target zone. Within hours, the optical telescopes found it, a new bright point of light in a galaxy called NGC 4993, located about 130 million light-years away in the constellation Hydra. The light was coming from the location where the gravitational waves and the gamma-ray burst had originated. This was the electromagnetic counterpart, the visible signature of the merger. The announcement was made on October 16, 2017, nearly 2 months after the detection. By that time, more than 70 observatories around the world had contributed data. The event was designated GW170817, named for the date it was detected. It was the first time in history that a single astrophysical event had been observed in both gravitational waves and electromagnetic radiation. The term for this is multi-messenger astronomy, using multiple types of signals, multiple messengers, to study the same event. The gravitational wave signal told astronomers the masses of the two neutron stars, roughly 1.1 to 1.6 solar masses each, and the distance to the merger, about 130 million light-years. The gamma-ray burst told them that the collision had produced a relativistic jet, a narrow beam of matter and radiation moving at close to the speed of light. The optical and infrared light, which appeared hours after the merger and persisted for weeks, told them something else. The collision had produced a kilonova. A kilonova is different from a supernova. A supernova is the explosion of a star. A kilonova is the explosion of a neutron-star merger. When two neutron stars collide, the impact is so violent that a significant fraction of their mass is ejected into space. Not all of it. Much of the material falls into the black hole or hypermassive neutron star that forms from the merger. But a small amount, roughly a few hundredths of a solar mass, gets flung outward at high speeds. That material is incredibly neutron-rich, much more so than anything found in a supernova. And within seconds, the free neutrons start getting captured by atomic nuclei in a process called rapid neutron capture, or the R process. The R process is how the universe makes the heaviest elements. Gold, platinum, uranium, thorium, all the elements heavier than iron that cannot be produced by normal stellar fusion, are thought to be created in environments where neutrons are extremely abundant and can be rapidly added to nuclei before the nuclei have time to decay. For decades, the site of the R process was debated. Supernovae were the leading candidate, but detailed models struggled to produce the right conditions. Neutron-star mergers were another candidate, but there was no direct evidence. GW170817 provided that evidence. The optical and infrared light from the kilonova showed spectral signatures consistent with heavy elements. The light was dominated by lanthanides, a group of elements near the bottom of the periodic table, which are produced in abundance during the R process. The brightness and colour of the light matched theoretical predictions for a kilonova, powered by the radioactive decay of freshly synthesized heavy elements. The conclusion was inescapable. Neutron star mergers produce heavy elements. A significant fraction of the gold, platinum and uranium in the universe, including the gold in any jewellery you might be wearing, was forged in collisions like this one. The ejected material glows because the newly formed radioactive isotopes decay, releasing energy. The glow starts bright in the blue and ultraviolet, then shifts to red and infrared as the material expands and cools. The light curve, the plot of brightness over time, follows a predictable pattern based on how much material was ejected and what elements it contains. The observations of GW170817 match the predicted light curve almost perfectly. The event also provided a new way to measure the expansion rate of the universe. Because the gravitational wave signal gives a direct measurement of the distance to the source, and because the optical observations identified the host galaxy and allowed a measurement of the galaxy's redshift, astronomers could combine the two to calculate the Hubble constant, the rate at which the universe is expanding. The result was about 70 kilometers per second per megaparsec, sitting right in the middle of the tension between the Planck satellite measurement and the supernova-based measurement. One event is not enough to resolve the Hubble tension, but it showed that gravitational wave observations could contribute to the effort. Future detections of neutron star mergers will add more data points and help pin down the true value. The story of GW170817 is a story of preparation meeting opportunity. The gravitational wave detectors had been under development for decades. The electromagnetic follow-up infrastructure, the networks of telescopes and satellites coordinated to respond to gravitational wave alerts, had been built over years of planning and testing. When the signal arrived, the system worked. The alert went out, the telescopes responded, the data poured in. And the result was a comprehensive picture of one of the most energetic events in the universe, captured in unprecedented detail across multiple wavelengths and messengers. One detail of the detection that has not received as much attention outside the specialist community is how close the event came to being missed. The signal arrived on August 17th. The LIGO detectors had only just resumed observations after a period of downtime for upgrades. Virgo had joined the network only a few weeks earlier. If the merger had happened a month earlier, Virgo would not have been online, and the localization of the source would have been much worse. If it had happened a few months earlier, LIGO would still have been offline. The timing was, in a sense, lucky. But the luck was earned, the detectors were ready, the teams were ready, and when the opportunity came, they did not miss it. There is a second type of gravitational wave detection that operates on completely different timescales and uses completely different instruments. Instead of kilometre-scale interferometers, it uses pulsars. Specifically, it uses the most stable pulsars in the galaxy, millisecond pulsars, as a kind of galactic-scale gravitational wave detector. The technique is called pulsar timing, and the arrays of pulsars monitored for this purpose are called pulsar timing arrays. The idea is simple in principle. Millisecond pulsars emit pulses with extraordinary regularity. By timing the arrival of those pulses over months and years, astronomers can build a model of each pulsar's rotation and predict when future pulses will arrive. If a gravitational wave passes through the space between Earth and a pulsar, it stretches and compresses spacetime, causing the pulses to arrive slightly early or slightly late compared to the prediction. The deviations are tiny, measured in nanoseconds, but they are detectable if you monitor enough pulsars for long enough. Pulsar timing arrays are sensitive to gravitational waves with much longer wavelengths than LIGO can detect. LIGO observes waves with frequencies of tens to thousands of hertz, corresponding to wavelengths of thousands to hundreds of kilometers. Pulsar timing arrays observe waves with frequencies of nanohertz, one cycle every few years, corresponding to wavelengths of light years. These are gravitational waves from much more massive sources, not stellar mass black holes or neutron stars, but supermassive black holes, the kind that sit at the centers of galaxies and weigh millions or billions of solar masses. When two galaxies merge, their central supermassive black holes eventually sink to the center of the merged galaxy and form a binary system. Over millions of years, the binary loses energy through gravitational wave emission, and the two black holes spiral closer together. For most of that in spiral, the gravitational waves they emit are too weak to detect. But in the final stages, when the black holes are separated by only a few light years and orbiting each other every few years, the gravitational waves become strong enough to affect the timing of pulsar signals across the galaxy. The North American Nanohertz Observatory for Gravitational Waves, or NANOGrav, is a collaboration that has been monitoring dozens of millisecond pulsars since 2007. In June 2023, NANOGrav announced that they had detected evidence for a low-frequency gravitational wave background. Not a single chirp from one binary, but a stochastic background, a kind of hum produced by the cumulative effect of many supermassive black hole binaries scattered across the universe, all emitting gravitational waves at slightly different frequencies. The detection was based on 15 years of data. The signal showed up as correlated deviations in the pulse arrival times of pulsars separated by large distances across the sky. The pattern of correlations matched the prediction for a gravitational wave background. The amplitude of the signal suggested that the background is dominated by black hole binaries with masses in the range of hundreds of millions to billions of solar masses orbiting each other every few years at distances of billions of light years. This is not the same kind of detection as LIGO's. LIGO detects individual events, discrete chirps from mergers happening in real time. NANOGrav detects an ensemble signal, the combined noise from countless binaries spread across cosmic time. It is like the difference between hearing a single voice in a quiet room and hearing the murmur of a crowd. The individual voices blur together, but the overall sound is unmistakable. The NANOGrav result is still being debated. Some researchers argue that the signal could include contributions from other sources, not just black hole binaries. Cosmic strings, hypothetical one-dimensional defects in spacetime left over from the early universe, could produce a similar background. Phase transitions in the early universe, moments when the vacuum state of the universe changed suddenly, could also produce gravitational waves that would show up in pulsar timing data. The dominant contribution is almost certainly from black hole binaries, but the presence of additional components cannot be ruled out yet. Other pulsar timing array collaborations around the world have reported similar results. The European Pulsar Timing Array, the Parkes Pulsar Timing Array in Australia, the Indian Pulsar Timing Array, and the Chinese Pulsar Timing Array have all found evidence for the same low-frequency background. The signals are consistent across collaborations, which strengthens the case that the detection is real. In 2023, the International Pulsar Timing Array, a coalition of these collaborations, released a combined analysis that increased the statistical significance of the detection. The implications are profound. If the background is dominated by supermassive black hole binaries, it provides a new way to study galaxy mergers and the growth of black holes over cosmic time. The amplitude and spectrum of the background depend on how many binaries exist, how massive they are, and how their population has evolved over billions of years. By measuring the background precisely, astronomers can constrain models of galaxy formation and black hole growth. There is also the possibility that pulsar timing arrays will detect individual loud binaries standing out above the background. These would be nearby supermassive black hole binaries, possibly only a few hundred million light-years away, in the final stages before merging. Detecting individual binaries would allow precise measurements of their masses, distances, and orbital parameters. It would also provide advance warning of an impending merger, allowing electromagnetic telescopes to monitor the system and search for any associated emission. The detection of gravitational waves, whether from LIGO or from pulsar timing arrays, has opened a new window on the universe. For most of human history, astronomy was done with light. Visible light first, then radio, infrared, ultraviolet, X-rays, gamma rays, each new wavelength revealing phenomena that had been invisible before. But all of those are forms of electromagnetic radiation, and electromagnetic radiation has limits. It can be absorbed, scattered, or blocked by intervening material. Gravitational waves are different. They pass through matter almost without interaction. A gravitational wave produced by a neutron star merger can travel for billions of years across the universe and arrive at Earth carrying information about the event that no electromagnetic signal could preserve. The multi-messenger approach, combining gravitational waves with electromagnetic observations, provides a more complete picture than either method alone. The gravitational waves tell you the masses, the orbital dynamics, the energy released. The electromagnetic signals tell you about the environment, the material ejected, the jets produced, the elements synthesized. Together they allow a reconstruction of the event in far greater detail than was possible before. GW170817 was the first such event. It will not be the last. LIGO and Virgo are continuing to observe, and they are being joined by new detectors. KGRA, a gravitational wave observatory in Japan, came online in 2020 and is now part of the network. LIGO India is under construction and will add a fifth detector to the global network, improving the localization of sources and increasing the detection rate. In the next decade, the number of detected neutron star mergers is expected to reach dozens or even 100 per year. Each detection will add to the catalogue of kilonovae, the explosive events that produce heavy elements. Astronomers will be able to study how the kilonova light curves vary depending on the masses of the merging neutron stars, the amount of material ejected, and the composition of that material. Over time, this will lead to a detailed understanding of how the R process operates in nature, and how much of the heavy element inventory of the universe comes from neutron star mergers versus other sources. The detection of gravitational waves has also provided new tests of general relativity. The theory predicts that gravitational waves should travel at the speed of light. The arrival of the gravitational wave signal from GW170817 within seconds of the gamma ray burst confirmed that prediction to extraordinary precision. If gravitational waves travelled at a different speed than light, the two signals would have been separated by hours or days, not seconds. The agreement rules out a wide range of alternative theories of gravity that predict different propagation speeds. Another prediction of general relativity is that gravitational waves should carry energy away from the source. The inspiral of a binary neutron star system is driven by the loss of orbital energy to gravitational wave emission. The rate at which the orbit shrinks matches the predictions of general relativity with extraordinary precision. This was first demonstrated in the 1970s with the Hulse-Taylor binary pulsar, which provided indirect evidence for gravitational waves. GW170817 provided direct evidence, and the agreement with theory is even tighter. There are still mysteries. The fate of the material left behind after a neutron star merger is not fully understood. Some of the material falls into the black hole that forms from the merger. Some is ejected into space and produces the kilonova. But what happens in between? Does a temporary hypermassive neutron star form spinning hundreds of times per second and held up by centrifugal force before collapsing into a black hole? Or does the collapse happen immediately? The answer depends on the equation of state of neutron star matter, the relationship between pressure and density at extreme conditions. Observations of kilonovae, combined with gravitational wave data, are helping to constrain that equation of state. The equation of state is one of the biggest open questions in neutron star physics. It determines how large a neutron star can be for a given mass. It determines whether the core is made of neutrons or quark matter. It determines how stiff or soft the material is, which affects how the star deforms under tidal forces during a merger. Every new observation of a neutron star, whether through gravitational waves, X-rays or timing, adds a piece to the puzzle. The multi-messenger observation of GW 170817 was not just a scientific achievement, it was a logistical one. Coordinating 70 observatories around the world, from space-based gamma-ray telescopes to ground-based optical telescopes to radio dishes, required years of planning. Automated alert systems had to be built, communication protocols had to be established. Observing schedules had to be flexible enough to respond to alerts on short notice. When the event happened, the system worked. The alert went out. The telescopes responded. The data came in, and the result was a dataset rich enough to answer questions that had been open for decades. The story of gravitational wave astronomy is far from over. LIGO, Virgo and Kagra are continuing to improve their sensitivity. The detection rate is increasing, new types of sources are being discovered, and the pulsar timing arrays are just beginning to map the low-frequency gravitational wave sky. In the coming years, the field will move from detecting individual events to performing population studies, mapping the distribution of neutron star and black hole masses, measuring the rate of mergers as a function of cosmic time, and using gravitational waves to probe the expansion history of the universe. But there is another type of explosion that neutron stars might be involved in. Not a merger, not a kilonova, something faster, something brighter, something that appears without warning, flares to a brilliance that rivals an entire galaxy, and then vanishes in less time than it takes to read this paragraph. These are the luminous fast blue optical transients, or LFBOTs, and they are among the strangest explosions ever observed. Some astronomers think they might be related to neutron stars, others are not so sure, but the events are so extreme, so far outside the normal behaviour of supernovae and other known transients, that they demand an explanation. And the search for that explanation is leading researchers into territory that feels less like established astrophysics and more like educated guessing. The first hint that something unusual was happening came from automated sky surveys. Over the past 2 decades, astronomy has shifted from pointing telescopes at specific targets to scanning the entire visible sky on a regular basis, looking for anything that changes. New stars that appear where there were none before, old stars that suddenly brighten or fade, asteroids drifting across the background of distant galaxies. The surveys generate enormous amounts of data, and most of what they find is mundane. Known variable stars doing what known variable stars do. Distant supernova, dozens per night, exploding right on schedule in galaxies billions of light years away. But every so often the algorithms flag something that does not fit any known category. Something too bright, something too fast, something wrong. In June 2018, the Asteroid Terrestrial Impact Last Alert System, ATLAS, a survey designed primarily to find asteroids that might pose a threat to Earth, detected an optical transient in a galaxy about 200 million light-years away. The object was designated a 2018 Cow, and within hours it had picked up a nickname, the Cow. The name stuck because the explosion was so bizarre that calling it by its formal designation felt too dry. This was not a normal supernova. This was something else. The Cow rose to peak brightness in less than 2 days. 2 days. Most supernovae take weeks to reach maximum light. The Cow got there before most telescopes even had time to respond to the alert. The peak luminosity was about 100 times brighter than a typical supernova, putting it in the range of what astronomers call superluminous supernovae, the brightest exploding stars known. But superluminous supernovae are powered by radioactive decay of nickel and cobalt produced in the explosion, and that process takes time. The light curves of superluminous supernovae rise over weeks and fade over months, The cow peaked in 2 days and started fading almost immediately. By the time most follow-up observations began, the cow was already on its way down. The spectrum was strange. Early spectra showed no clear lines, just a smooth blue continuum. Blue means hot. The surface temperature of the emitting material was tens of thousands of degrees, much hotter than a normal supernova at the same stage. As the cow faded, weak features began to appear in the spectrum, but they did not match the expected signatures of hydrogen, helium, or the heavy elements typically seen in supernova ejecta. The cow was not behaving like any known type of stellar explosion. Then the X-rays showed up. The Chandra X-ray Observatory pointed at the cow a few days after peak and detected strong X-ray emission. X-rays from supernovae are not unheard of, but they're usually faint and appear weeks or months after the explosion when the expanding shockwave starts interacting with surrounding material. The cow was producing bright X-rays almost immediately, and the X-ray luminosity was comparable to the optical luminosity. That is not normal. For most supernovae, the X-ray emission is a tiny fraction of the total energy output. The cow was pumping out X-rays at a rate that suggested something other than radioactive decay was powering the explosion. Radio observations added another layer of weirdness. The Very Large Array in New Mexico detected radio emission from the cow, and the radio-light curve showed rapid variability. The brightness changed on timescales of days, sometimes hours. Radio emission from supernovae is produced when the expanding debris crashes into surrounding material, heating it and accelerating electrons to relativistic speeds. That process is typically gradual, and the radio-light curve evolves slowly over weeks or months. The cow's radio emission was changing so fast that it implied the emitting region was very small, and the energy injection was rapid and ongoing. Putting it all together, the picture that emerged was deeply strange. The cow had released an enormous amount of energy comparable to a superluminous supernova, but on a timescale 10 times faster. The explosion was hot, producing bright blue and ultraviolet light. It was generating X-rays and radio waves at luminosities that standard supernova models struggled to explain. And it was doing all of this in a galaxy that showed no signs of unusual activity. No active galactic nucleus, no recent star formation burst, nothing that would hint at an exotic progenitor star. Theorists scrambled to explain it. The leading hypothesis involved a central engine, some kind of compact object at the heart of the explosion that was continuously injecting energy into the expanding debris. A black hole accreting material from the fallback of the explosion could in principle do it. As material falls into the black hole, it heats up and emits radiation, and some of that radiation could escape and power the light curve. But the timescales were tight. The cow faded so quickly that the engine would have to inject most of its energy in the first few days and then shut off or fade rapidly. That is possible, but it requires fine-tuning. Another possibility was a magnetar, a neutron star with an extraordinarily strong magnetic field. Magnetars are born spinning rapidly, and as they spin down, they release energy. That energy can be deposited into the surrounding ejecta, heating it and causing it to glow. Magnetar-powered supernovae had been proposed before as an explanation for superluminous supernovae, and the cow looked like it could fit the model. The rapid rise and fall of the light curve could be explained if the magnetar was born with an extremely high spin rate, and lost most of its rotational energy in the first few days. The X-rays could be explained by emission from the magnetar's magnetosphere, or by shocks driven into the ejecta by the magnetar wind. The magnetar model had appeal. It explained the rapid evolution, the high luminosity, and the presence of X-rays. It also explained why the event was so rare. Not all supernovae produce magnetars, and even among those that do, only a small fraction would produce magnetars with the specific combination of spin rate and magnetic field strength needed to power something like the cow. The cow could be a glimpse of a rare endpoint of stellar evolution, a supernova where the core collapsed into a neutron star that then spun down so rapidly that it lit up the sky for a few days before fading into obscurity. But the magnetar explanation had problems. The X-ray and radio emission from the cow showed features that did not quite fit the magnetar model. The variability was too rapid. The spectrum was too hard, meaning the X-rays were too high in energy compared to what you would expect from a magnetar wind interacting with slowly expanding ejecta. And the radio emission suggested the presence of a relativistic outflow, Possibly a jet, which is not a standard feature of magnetar-powered supernovae. So maybe it was not a supernova at all. Maybe it was a tidal disruption event. When a star wanders too close to a black hole, the tidal forces tear the star apart. The debris forms an accretion disk around the black hole, and as the material spirals inward, it heats up and emits radiation. Tidal disruption events are known to produce bright flares of optical, ultraviolet, and X-ray light. Most tidal disruption events involve supermassive black holes at the centres of galaxies, and the flares last for months or years as the debris slowly accretes. But if the black hole was smaller, say an intermediate mass black hole weighing a few thousand solar masses, the timescales could be faster. A smaller black hole has a smaller tidal radius, so the debris is more tightly bound and accretes more quickly. That could in principle produce a fast, bright transient like the cow. The tidal disruption model explained the rapid evolution and the presence of X-rays. It struggled to explain the lack of hydrogen in the spectrum. If a normal star was disrupted, the debris should contain hydrogen, and that hydrogen should produce strong emission lines in the spectrum. The cow showed no such lines. You could get around this by invoking the disruption of a helium star, a star that has already lost its hydrogen envelope, but helium stars are rare, and the probability of one being disrupted by an intermediate mass black hole is vanishingly small. Possible, but not satisfying. The debate over the cow's origin was still ongoing when the next one showed up. In December 2019, Atlas detected another fast blue transient, this one designated a 2019 CAD. It was not as bright as the cow, but it evolved on similar timescales and showed similar spectral features. Then came at 2020 MRF in April 2020, then at 2020 Exond in December 2020. By 2021, it was clear that the cow was not a one-off. There was a population of these things, and they were showing up a few times per year in surveys that covered large fractions of the sky. The class was formalized: luminous, fast blue optical transients, LFBOTs. Pronounced LFBOTs by some, ELFBOTs by others, and simply referred to as fast blue transients by those who find acronyms exhausting. The defining characteristics are the speed, the blue colour, and the luminosity. Rise times of a few days. Peak luminosities that can reach or exceed those of superluminous supernovae. Hot, featureless early spectra, and in many cases bright X-ray and radio emission. Not all LFBOTs show all of these features, but the pattern is consistent enough that they are treated as a distinct class. As more LFBOTs were discovered, the diversity within the class became apparent. Some are brighter than the cow, some are fainter. Some show strong X-ray emission, others do not. Some have hints of spectral lines that suggest specific elements in the ejector, others remain featureless. The variations suggest that LFBOTs are not a single phenomenon, but a family of related phenomena, possibly with different progenitor systems or different physical mechanisms driving the explosions. One of the brightest LFBOTs discovered so far is 82024 WPP. This object was detected in early 2024 and reached a peak luminosity about 5 to 10 times brighter than the cow. The total energy radiated in the first 45 days exceeded 10 to the 51 ergs, which is the canonical energy of a supernova explosion. In other words, this object released as much energy in its first month and a half as an entire supernova releases over its entire evolution, and it did so with a light curve that rose to peak in less than a week and faded to half-peak brightness in about the same time. The existence of objects like at 2024 WP pushes the energy budget to uncomfortable levels. Radioactive decay cannot explain it. There is simply not enough nickel produced in any plausible supernova to power a light curve that bright and that fast. The only way to get that much energy into the ejector that quickly is to have a central engine continuously injecting power, and the engine has to be powerful. Not just a typical black hole or magnetar, but something operating at or near its theoretical limits. The central engine hypothesis is now the leading explanation for most LFBOTs. But what kind of engine? Black holes and magnetars are the two main candidates, and the debate over which one is correct hinges on the details of the observations and the assumptions you make about the explosion geometry and the surrounding environment. Black holes have the advantage of being able to release enormous amounts of energy through accretion. Material falling into a black hole can convert up to about 10% of its rest mass into energy, making accretion one of the most efficient energy-generating processes in the universe. If a black hole forms in the centre of a supernova and immediately starts accreting the fallback material. It could in principle power a bright transient. The X-rays observed in many LFBOTs fit naturally with accretion onto a black hole. Accretion disks around black holes are known to produce hard X-ray spectra, and the rapid variability in the X-ray light curves is consistent with variability in the accretion rate. But black holes face a problem with the optical light. The optical emission in LFBOTs is not coming directly from the accretion disk. It is coming from the expanding debris, which is being heated by some external source. If the black hole is injecting energy into the ejector, it has to do so through radiation or through a wind or jet. Radiation from the accretion disk can in principle heat the ejector, but the ejector is optically thick in the early stages, meaning the radiation has to diffuse outward through the debris before it can escape. That diffusion takes time, and it tends to smooth out any rapid variations in the energy injection. The fast evolution of LFBOTs suggests that the diffusion time is very short, which means the ejector must be thin and low mass. But if the ejector is low mass, where did it come from? Most supernovae eject several solar masses of material. LFBOTs seem to require much less. Magnetars, on the other hand, do not face the same diffusion problem. A magnetar injects energy into the ejector through its spin down, and the energy is deposited throughout the volume of the debris, not just at the centre. This can heat the ejector more uniformly and produce a light curve that rises and falls on shorter timescales. The magnetar model also explains why LFBOTs are rare. Only a small fraction of core-collapsed supernovae produce magnetars, and only a subset of those magnetars have the right initial spin rate to power an LFBOT. Recent theoretical work has explored a specific magnetar scenario in which the newly formed neutron star undergoes a phase transition in its interior shortly after birth. The idea is that the neutron star is initially supported by neutron degeneracy pressure, but as it cools or as material falls back onto it, the core undergoes a transition to a hybrid state containing quark matter or some other exotic phase. The phase transition releases energy, and it can also change the structure of the star in a way that affects its magnetic field and rotation. If the phase transition happens within a few days of the supernova, it could inject a burst of energy into the surrounding debris and produce the rapid light curve characteristic of LFBOTs. This model is speculative. Phase transitions in neutron star interiors are still poorly understood, and there is no direct observational evidence that they happen at all. But the model has the advantage of explaining both the rapid evolution and the diversity of LFBOTs. Different initial neutron star masses and spins would lead to different phase transition timescales and energies, producing a range of observed light curves and luminosities. Another piece of the puzzle is the geometry. Some LFBOTs show evidence for a jet, a narrow relativistic outflow that punches through the expanding debris and escapes into space. If the jet is pointed toward Earth, we see a bright flare of gamma rays or X-rays. If it is pointed away, we see only the isotropic emission from the debris. The presence or absence of a jet could explain some of the diversity in the observed properties of LFBOTs. Objects with jets pointed toward us would be brighter in X-rays and would show harder spectra. Objects with jets pointed away would be fainter in X-rays and would look more like ordinary supernovae, albeit fast and blue ones. The jet hypothesis is supported by the radio observations. Many LFBOTs show bright, rapidly variable radio emission, which is a hallmark of synchrotron radiation from relativistic electrons in a jet or outflow. The radio light curves often peak days to weeks after the optical peak, which is consistent with the jet breaking out of the ejector and becoming visible once the debris has thinned enough to be transparent to radio waves. But not all LFBOTs show radio emission. Some are radio quiet, at least at the sensitivity limits of current telescopes. This could mean that not all LFBOTs produce jets, or it could mean that the jets in those cases are pointed away from us, or are weak enough that the radio emission falls below the detection threshold. Either way, the presence of radio emission in some LFBOTs but not others adds another layer of complexity to the picture. The observational challenge with LFBOTs is that they are rare and they fade quickly. By the time a discovery alert goes out and telescopes start responding, the object may already be past peak brightness. Follow-up observations require fast response times and coordination across multiple wavelengths. Optical telescopes need to catch the early rise and peak. X-ray telescopes need to observe within the first few days to catch the hard X-ray emission before it fades. Radio telescopes need to monitor the object over weeks to catch the late-time radio emission. Each wavelength provides a piece of the puzzle, But getting all the pieces requires a level of coordination that is difficult to achieve, especially for objects that are discovered in distant galaxies where the light travel time means we are always seeing the explosion days or weeks after it actually happened. One of the frustrations in the field is that LFBOTs are extragalactic. They happen in other galaxies hundreds of millions or even billions of light years away. That means we cannot resolve the explosion site or study the environment in detail. We cannot see the progenitor star before it exploded. We cannot measure the mass or composition of the ejector directly. We are limited to studying the light curve and the spectrum, and those only give indirect information about what is happening physically. If an LFBOT happened in the Milky Way, it would be a transformative event. We would see it brightening in real time. We would have multi-wavelength coverage from the moment the light first appeared. We could measure the distance precisely, resolve the explosion site, study the surrounding nebula, and possibly even detect neutrinos or gravitational waves if the explosion involved a compact object merger or core collapse. But the rate of LFBOTs is low enough that the probability of one happening in our galaxy in any given century is small. We are stuck observing them at cosmological distances, where the details are blurred by distance and time. Despite the challenges, the field is moving forward. Each new LFBOT adds to the sample. Each one is followed up with as much data as the telescopes can provide. The light curves are being catalogued, the spectra are being analysed, the X-ray and radio properties are being compared across the sample. Patterns are starting to emerge. The fastest LFBOTs tend to be the bluest. The brightest LFBOTs tend to show the strongest X-ray emission. The ones with jets tend to show rapid radio variability. These patterns are clues. They constrain the models and rule out some possibilities. One thing that is becoming clear is that LFBOTs are not all the same. There is a range of properties, and that range probably reflects a range of progenitor systems or explosion mechanisms. Some LFBOTs may be magnetar-powered supernovae. Some may be tidal disruptions of stars by intermediate mass black holes. Some may be the result of mergers between white dwarfs and neutron stars or between two white dwarfs in configurations that produce unusual outcomes. The field is still in the phase of gathering data and trying to sort the population into subclasses. The role of neutron stars in LFBOTs is still uncertain. The magnetar model remains one of the leading explanations, but it is not the only one, and it does not fit all the observations cleanly. The phase transition model is intriguing, but speculative. The black hole accretion model is more conservative but faces its own challenges. The tidal disruption model works for some objects but not others. No single model explains the entire class. What we can say is that LFBOTs represent some of the most extreme transient events in the universe. They release as much energy as supernovae but on timescales 10 times faster. They reach temperatures high enough to produce intense ultraviolet and X-ray emission. They produce jets or outflows that accelerate particles to relativistic speeds. And they do all of this in systems that are rare enough that we only catch a few per year in surveys covering the entire visible sky. The discovery of LFBOTs has forced astrophysicists to expand their models of what stellar explosions can do. For decades, supernovae were the gold standard for transient events: bright, long-lived, powered by radioactive decay, and relatively well understood. LFBOTs do not fit that mold. They are too fast, too blue, too energetic, and too weird. They require engines, not just passive decay. They require extreme conditions, not just the collapse of a massive star. They require physics at the edge of what neutron stars and black holes can produce. If neutron stars are involved, they are not behaving like normal pulsars or even like normal magnetars. They are operating at their limits, converting rotational energy into radiation and kinetic energy on timescales of days, then fading back into the dark. If black holes are involved, they are accreting at near Eddington rates, the theoretical maximum rate at which a black hole can swallow material before the radiation pressure pushes the infalling gas away. Either way, LFBOTs are probing the most extreme states of matter and energy that nature allows. The fact that we can observe these events at all is a testament to how sensitive modern telescopes have become. Atlas, the survey that discovered the cow, was designed to find asteroids. The fact that it also finds the brightest explosions in distant galaxies is a side effect of its wide field of view and rapid cadence. Other surveys, like the Zwicky Transient Facility and the upcoming Vera Rubin Observatory, are finding even more transients at even greater distances. The rate of discovery is accelerating. In a few years, We will be finding LFBOTs at a rate of dozens per year, possibly more. Each one will be a data point. Each one will add to the statistical sample, and eventually the patterns will become clear enough that the models will converge on a consensus. But we are not there yet. The field is still in the Wild West phase, where new discoveries are happening faster than theory can keep up. Theorists are proposing models, observers are testing them, and the models are being revised or discarded based on the data. It is messy, it is exciting, and it is exactly how science is supposed to work. You start with an anomaly, something that does not fit the existing framework. You gather more data, you propose explanations, you test them, and slowly, over years or decades, the picture comes into focus. LFBOTs are a reminder that the universe is not done surprising us. Neutron stars are not just pulsars. Black holes are not just quiet sinks of matter. Explosions are not just supernovae. There is a wider range of phenomena out there, and we are only beginning to map it. The cow was a wake-up call. It told us that there are things happening in the universe that we had not accounted for, things that do not fit neatly into the categories we had built over the past century of astrophysics. And the more we look, the more we find. The story of LFBOTs is still being written. We know what they are, in the sense that we can define them by their observational properties. We do not yet know what they are in the sense of understanding the physical mechanism that produces them. That understanding will come. It always does. But it takes time, and it takes data, and it takes the willingness to sit with uncertainty long enough for the patterns to emerge. In the meantime, the transient sky keeps flickering. Somewhere out there, a few 100 million light-years away, another LFBOT is exploding. It is rising to peak brightness in a matter of days, glowing blue-white, pouring out X-rays and radio waves, and then fading back into the dark. The light from that explosion is on its way to Earth right now, travelling through space at the speed of light. In a few 100 million years it will arrive. A telescope will catch it, an algorithm will flag it, and another astronomer will stare at the light curve and wonder what the hell just happened. Because that is what neutron stars do. They keep finding new ways to remind us that we do not have all the answers yet, and every time we think we have the picture figured out, they find a new way to break the frame. Which brings us to the deepest question these objects raise. Not what they do, but what they mean. Because neutron stars are not just astronomical curiosities, they are laboratories. Natural laboratories operating under conditions we cannot reproduce anywhere else in the universe. And the experiments they're running, whether we understand them or not, are teaching us things about physics that we cannot learn any other way. Think about what we have covered. Neutron stars pack more mass than the Sun into a sphere the size of a city. They spin hundreds of times per second. They generate magnetic fields trillions of times stronger than anything on Earth. They produce beams of radiation so focused and so stable that we can use them as cosmic clocks. They spray antimatter into space at rates that challenge our models. They send out radio pulses on timescales that should not be possible. They collide with each other and forge the heaviest elements in the universe, while simultaneously ringing spacetime like a bell. And occasionally they explode in ways that make supernovae look boring. Every single one of these phenomena is pushing the boundaries of known physics. Not in the sense of breaking the laws, but in the sense of testing them in regimes where the equations become uncomfortable, where the approximations we use in everyday physics stop working, where the assumptions we make about how matter behaves, how gravity works, how particles interact, all of it gets squeezed into configurations so extreme that new behaviour emerges. The density of a neutron star is the most obvious example. 600 trillion times denser than water. Dense enough that atoms stop existing as distinct objects. Dense enough that the distinction between an atom and its neighbour ceases to be meaningful. At those densities, matter enters a regime where the rules governing how particles arrange themselves are dictated not by chemistry, not even by normal nuclear physics, but by quantum mechanics at a scale usually reserved for individual particles. This is why physicists talk about neutron stars as laboratories, because the conditions inside a neutron star cannot be recreated in any particle collider or laboratory on Earth. The Large Hadron Collider at CERN can smash protons together at energies high enough to briefly create conditions similar to those a fraction of a second after the Big Bang. But it cannot sustain those conditions. The collisions last for a tiny fraction of a second, and then the debris flies apart. A neutron star, on the other hand, has been sitting at densities exceeding nuclear density for thousands, millions, or in some cases billions of years. It is a stable configuration. It is not a fleeting collision. It is an object you can observe, measure, and study in detail over time. In June 2025, about 50 experts gathered at CERN for a workshop titled Neutron Stars as Precision Laboratories for Fundamental Physics. The goal was to discuss how observations of neutron stars can constrain theories of matter, gravity, and the forces that govern the universe at the smallest scales. The fact that this workshop was held at CERN, the world's premier particle physics laboratory, is telling. Particle physicists are used to building bigger and bigger colliders to probe smaller and smaller scales, but there is a limit to how big you can build a collider, and there is a limit to how much energy you can pack into a beam of particles. Neutron stars do not have those limits. Nature has already built the experiment. Our job is just to observe it and figure out what it is telling us. One of the central questions discussed at that workshop is the equation of state of neutron star matter. The equation of state is the relationship between pressure and density for a given material. For water, the equation of state is simple. For air, it is a bit more complicated. For matter at nuclear densities, it is deeply uncertain. We know that at low densities, matter is made of protons and neutrons held together by the strong nuclear force. We know that at extremely high densities, matter might dissolve into a soup of quarks and gluons, the fundamental particles that make up protons and neutrons. But the transition between those two regimes, the point at which neutrons stop being neutrons and start being quark soup, is one of the biggest open questions in nuclear physics. The equation of state determines how large a neutron star can be for a given mass. If the matter is stiff, meaning it resists compression strongly, then neutron stars can be larger. If the matter is soft, meaning it compresses easily, then neutron stars are smaller. Observations of neutron star masses and radii, combined with gravitational wave detections from neutron star mergers, are starting to constrain the equation of state. But the constraints are not tight enough yet to rule out all the possibilities. The range of allowed equations of state still includes models where the core is made entirely of neutrons, models where the core contains exotic particles called hyperons or delta isobars, and models where the core has undergone a phase transition to deconfined quark matter. Hyperons are baryons, particles made of 3 quarks, but instead of containing only up and down quarks like protons and neutrons, they contain strange quarks. Strange quarks are heavier than up and down quarks, and they are unstable in isolation. But at the densities in a neutron star core, strange quarks might become stable, and hyperons might form. If hyperons are present in significant numbers, they soften the equation of state because hyperons are less resistant to compression than neutrons. A neutron star with a hyperon core would be smaller for the same mass than a neutron star with a pure neutron core. Delta isobars are another possibility. These are excited states of nucleons, heavier and less stable, but possibly stable at neutron star densities due to the surrounding pressure. Their presence would also affect the equation of state, though the details depend on how they interact with the surrounding neutrons and how their population is distributed through the core. Quark matter is the most exotic possibility. If the density in the core exceeds a certain threshold, the strong force that holds neutrons together might no longer be able to contain the quarks inside individual neutrons. The quarks would deconfine, meaning they would no longer be bound into groups of 3. Instead, the entire core would become a sea of quarks and gluons, a quark-gluon plasma similar to what existed in the first microseconds after the Big Bang. A neutron star with a quark matter core would not technically be a neutron star anymore. It would be a hybrid star, with a quark core surrounded by a neutron mantle, or possibly a strange star if the entire interior converted to strange quark matter. The possibility of strange quark matter is particularly unsettling, because some models suggest it might be more stable than ordinary nuclear matter. If that is true, then any neutron star that forms a quark core could trigger a runaway conversion process, where the strange matter converts the surrounding neutrons into more strange matter. The process would propagate outward from the core until the entire star had converted. And if a strange star collided with a normal neutron star, the strange matter could infect the normal star, converting it as well. This is pure speculation, and there is no observational evidence that it happens, but the equations allow it. The fact that we do not know what is in the core of a neutron star is not a failure of physics. It is a consequence of the fact that the core is inaccessible to direct measurement. We cannot drill into a neutron star. We cannot take a sample. We can only observe the star from the outside and infer what is happening inside based on how the star behaves. The mass and radius tell us about the equation of state. The cooling rate tells us about the thermal properties of the interior. The way the star deforms under tidal forces during a merger tells us about the stiffness of the material. Each observation adds a constraint, and slowly the picture comes into focus. Gravitational wave detections have been particularly useful. The signal from GW170817, the neutron star merger detected in 2017, included information about how the neutron stars deformed as they spiraled toward each other. That deformation is quantified by something called the tidal deformability, a number that depends on the equation of state. A stiff equation of state produces stars that resist deformation, resulting in low tidal deformability. A soft equation of state produces stars that deform easily, resulting in high tidal deformability. The measured tidal deformability from GW170817 ruled out some of the stiffest and some of the softest equations of state, narrowing the range of possibilities. Future gravitational wave detections will continue to tighten the constraints. Each merger provides another data point, and as the network of gravitational wave detectors expands, the precision of the measurements will improve. Within a decade, we may have enough data to definitively determine whether neutron star cores contain only nucleons, or whether exotic matter is present. That determination will not just tell us about neutron stars, it will tell us about the strong force, about quantum chromodynamics, and about how matter behaves at densities that cannot be studied any other way. But the equation of state is not the only thing neutron stars can teach us. They are also probes of fundamental forces. General relativity, Einstein's theory of gravity, has been tested extensively in the weak field regime, the regime where gravity is relatively gentle. The orbit of Mercury, the bending of light by the Sun, the time dilation measured by GPS satellites, all of these are weak field tests, and general relativity passes them with flying colours. But neutron stars operate in the strong field regime, where gravity is so intense that space-time curvature is extreme. Testing general relativity in that regime is much harder, and it is where deviations from the theory, if they exist, are most likely to show up. Pulsar timing provides one of the best strong field tests. The orbital decay of the Hulse-Taylor binary pulsar, caused by energy lost to gravitational waves, matches the predictions of general relativity to within a fraction of a percent. More recent observations of other binary pulsars have extended those tests. Some systems contain a pulsar orbiting a white dwarf or another neutron star, and the precision with which the orbit can be measured allows tests of general relativity that are sensitive to effects that would be impossible to detect in the solar system. One such test is the measurement of the Shapiro delay, the time delay that light experiences when it passes through a gravitational field. In a binary pulsar system, the pulses from the pulsar have to pass through the gravitational field of the companion star before reaching Earth. The delay depends on the mass of the companion, and by measuring the delay, astronomers can weigh the companion star with extraordinary precision. The measured delays match the predictions of general relativity exactly, providing another confirmation of the theory in a strong field environment. Another test involves measuring the precession of the orbit. In Newtonian gravity, the orbit of a binary system is a perfect ellipse that does not change orientation over time. In general relativity, the orbit precesses, meaning the orientation of the ellipse slowly rotates. The rate of precession depends on the masses of the objects and the strength of the gravitational field. For the Hulse-Taylor pulsar, the precession rate is about 4 degrees per year, and the measured rate agrees with the predictions of general relativity to within measurement uncertainty. These tests are important because general relativity, for all its successes, is known to be incomplete. It does not play well with quantum mechanics. At very small scales, near the singularity inside a black hole or at the moment of the Big Bang, general relativity predicts infinities, which is physics speak for the theory breaks down. Physicists have been searching for a theory of quantum gravity, a framework that unifies general relativity with quantum mechanics, for nearly a century. No such theory has been confirmed yet. String theory is one candidate. Loop quantum gravity is another. But both are still speculative, and neither has made predictions that can be tested with current technology. Neutron stars might provide a way forward. They are not quite extreme enough to probe the Planck scale, the scale at which quantum gravity effects are expected to dominate. But they are close enough that subtle deviations from general relativity, if they exist, might show up in observations. Some modified theories of gravity predict that neutron stars should emit dipole gravitational radiation, a type of radiation not present in general relativity. Detecting such radiation would be a smoking gun for new physics. So far, no such radiation has been detected, but the searches are ongoing. The unification of gravity and quantum mechanics is not just an academic puzzle. It is one of the central unresolved questions in all of physics. General relativity describes gravity beautifully on large scales, from planets to galaxies to the entire universe. Quantum mechanics describes the behavior of particles beautifully on small scales, from atoms to quarks to the quantum vacuum. But the two theories use different mathematical frameworks and make incompatible assumptions about the nature of space and time. At some point, the two frameworks have to merge into a single consistent theory. Neutron stars, sitting at the intersection of extreme gravity and extreme density, are one of the best natural laboratories we have for exploring that intersection. And then there is dark matter, the invisible substance that makes up 85% of the matter in the universe, but has never been directly detected. We know dark matter exists because we can see its gravitational effects. Galaxies rotate faster than they should based on the visible matter alone. Galaxy clusters hold together despite not having enough visible mass to generate the required gravity. The cosmic microwave background shows patterns that can only be explained if dark matter was present in the early universe to seed the formation of structure. But we do not know what dark matter is made of. Decades of experiments have searched for dark matter particles, and so far they have come up empty. Neutron stars offer a new way to search. The idea is simple. If dark matter particles exist, some of them should be passing through neutron stars right now. Most would pass straight through without interacting, but a small fraction would scatter off the neutrons in the star, lose energy, and become gravitationally bound. Over time, those captured particles would accumulate in the core of the neutron star, forming a dense clump of dark matter at the centre. What happens next depends on what dark matter is. If dark matter particles are their own antiparticles, like some models predict, then the accumulated dark matter in the core could annihilate, converting mass into energy. That energy would heat the neutron star, raising its temperature above what it would otherwise be for a given age. Old, cold neutron stars are ideal targets for this search because they should have cooled to the point where they are barely glowing in X-rays. If an old neutron star is warmer than expected, it could be a sign that dark matter annihilation is heating it from the inside. In some more extreme scenarios, the accumulated dark matter could collapse into a tiny black hole at the centre of the neutron star. That black hole would then start accreting the surrounding neutron star material, growing slowly over time. Eventually, it could consume the entire neutron star from the inside out. The neutron star would appear normal from the outside for a long time, but eventually it would collapse into a black hole without producing a supernova or any other visible signal. The disappearance of neutron stars over time could in principle be used as an indirect detection method for dark matter, though this scenario requires dark matter to interact much more strongly with ordinary matter than most models predict. Recent studies have shown that neutron stars can probe dark matter in mass ranges that are difficult or impossible to access with ground-based detectors. Direct detection experiments on Earth are optimized for dark matter particles in the range of about 10 to 1000 gigaelectronvolts. But if dark matter is lighter than that, say in the range of a few hundred megaelectronvolts to a few gigaelectronvolts, most terrestrial detectors lose sensitivity. Neutron stars do not have that limitation. Because of their immense gravity and density, they can capture and accumulate dark matter particles across a much wider mass range. One study published in recent years argued that neutron stars could outperform direct detection experiments for sub-Geiger electron-volt dark matter in certain interaction channels. The study calculated how efficiently neutron stars capture dark matter as a function of particle mass and interaction strength, and found that for some parameter ranges, neutron stars are the most sensitive probes available. The challenge is that the signal, heating or changes in the neutron star structure, is subtle and requires precise measurements of neutron star temperatures and masses over long periods. The search for dark matter using neutron stars is still in its early stages. Most of the work so far has been theoretical, calculating the expected signatures and determining what kinds of observations would be needed to detect them. But as X-ray telescopes improve and as the census of nearby neutron stars grows, the observational side is catching up. In the next decade, dedicated surveys of old neutron stars may be able to place the strongest constraints yet on the properties of dark matter. Beyond the equation of state, beyond tests of general relativity, beyond dark matter, neutron stars are also teaching us about nuclear physics in ways that cannot be replicated in laboratories. The interiors of neutron stars are expected to contain superfluid neutrons and superconducting protons, quantum states of matter that have been studied in the lab at low temperatures, but never at the densities present in a neutron star. A superfluid is a state where a fluid flows without viscosity, meaning it can flow forever without losing energy to friction. A superconductor is a state where electric current flows without resistance. Both states are manifestations of quantum mechanics operating at macroscopic scales. The presence of superfluids and superconductors in neutron stars affects how they cool, how they respond to tidal forces, and how they transmit vibrations through their interiors. Starquakes, the sudden cracking of the neutron star crust, produce seismic waves that propagate through the star. If the interior contains superfluid layers, those waves behave differently than they would in a normal fluid. Observations of starquakes and their aftereffects, detected as changes in pulsar timing, or as bursts of X-rays, provide indirect evidence for the presence of superfluids. One of the most compelling pieces of evidence comes from pulsar glitches. Some pulsars, particularly young ones, occasionally experience sudden increases in their rotation rate. The star spins up by a tiny fraction, typically 1 part in a million or less, and then gradually relaxes back toward its pre-glitch rotation rate over days or weeks. The glitches are thought to be caused by the sudden transfer of angular momentum from a superfluid component in the interior to the solid crust. The superfluid, which is not coupled to the crust through friction, can rotate faster than the crust. When the difference becomes too large, the superfluid and the crust suddenly couple, transferring momentum and causing the glitch. Detailed observations of pulsar glitches, measuring how fast the star spins up and how quickly it relaxes, allow physicists to infer the properties of the superfluid. How much superfluid is present? How strongly is it coupled to the crust? What is the temperature of the superfluid and how does that affect its behavior? These are questions that can only be answered by observing neutron stars. No laboratory experiment can create a superfluid neutron fluid at nuclear densities. Nature has done it for us, and the pulsars are broadcasting the results. The same is true for magnetic fields. The strongest magnetic fields ever created in a laboratory are about a few hundred Tesla, achieved in specialized facilities that can sustain the field for a few milliseconds before the equipment explodes. Neutron stars, particularly magnetars, have magnetic fields 1 trillion times stronger, sustained for thousands or millions of years. At those field strengths, the vacuum itself becomes polarized, and particles behave in ways that are completely outside the realm of normal experience. Electrons forced to move perpendicular to the field lines spiral at relativistic speeds, emitting synchrotron radiation. The field is so strong that it affects the energy levels of atoms, distorting atomic spectra in ways that can be used to measure the field strength remotely. Observations of magnetars, particularly the X-ray spectra emitted during bursts, have provided the first measurements of how matter behaves in ultra-strong magnetic fields. The data match predictions from quantum electrodynamics, the theory that describes how light and matter interact but only barely. The field strengths in magnetars push quantum electrodynamics into a regime where higher-order corrections become important, corrections that are usually negligible in laboratory settings. Testing those corrections requires fields that no human technology can produce. Magnetars provide those fields for free. There's also the possibility that neutron stars are involved in processes we have not even thought of yet. The fact that objects like GPM J1839-10 exist, pulsing every 22 minutes in defiance of the Pulsar deathline, suggests that our models are incomplete. The fact that LFBOTs exist, exploding with luminosities that rival superluminous supernovae but on timescales 10 times faster, suggests that there are engines and mechanisms operating in the universe that we have not fully characterized. Neutron stars are implicated in both phenomena, but the details are murky. We have the observations, we have models that kind of work, but we do not have certainty. That is the state of the field. Neutron stars have gone from being theoretical predictions in the 1930s to being one of the most intensely studied classes of objects in all of astronomy. We have detected thousands of them. We have measured their masses and radii. We have watched them spin down over decades. We have detected their gravitational waves. We have caught the light from their collisions and used it to measure the expansion rate of the universe. We have used them to test general relativity in regimes where the theory is hardest to test. We have searched for dark matter in their cores. We have studied the superfluids and superconductors in their interiors. And we have used them to map the magnetic fields of the universe, to trace the production of heavy elements, and to probe the behavior of matter at densities that cannot be reached any other way. And after all of that, we still do not fully understand them. We do not know what is in the core. We do not know whether quark matter exists. We do not know how magnetars sustain their magnetic fields for so long. We do not know what powers ultra-long period radio transients. We do not know what produces LFBOTs. We do not know how much of the positron excess comes from pulsars, and how much comes from other sources. We do not know whether neutron star mergers are the only source of our process elements, or whether there are other sites we have not identified. We do not know whether dark matter is accumulating in neutron star cores, or passing through them unimpeded. And we do not know what the upper mass limit for a neutron star is, the point at which the degeneracy pressure finally fails and the star collapses into a black hole. These are not minor gaps in the picture. They are foundational questions about how matter behaves, how gravity works, and how the universe operates at its extremes, and they cannot be answered by building bigger colliders or running longer computer simulations. They can only be answered by observing neutron stars, by timing their pulses, by measuring their masses and radii, by detecting their gravitational waves, by catching their explosions and colonovae, by mapping their magnetic fields, by studying their spectra, by watching how they evolve over time. Each observation adds a piece to the puzzle. Each measurement narrows the range of possibilities, and slowly, over years and decades, the answers emerge. The tools are improving. Gravitational wave detectors are getting more sensitive. X-ray telescopes are getting sharper. Radio telescopes are scanning wider areas of the sky. Pulsar timing arrays are adding more pulsars and achieving better timing precision. Computer models are incorporating more physics and running at higher resolutions. The census of known neutron stars is growing. The rate of discovery is accelerating. And the interdisciplinary nature of neutron star research, bringing together nuclear physicists, particle physicists, astrophysicists, and gravitational wave experts, is producing collaborations that would have been unthinkable a generation ago. This is the frontier. Not the edge of the known universe, but the edge of known physics. Neutron stars sit at that edge, doing things that push every theory we have to its limits. They are laboratories built by nature, experiments running on timescales far longer than any human experiment could ever run, under conditions far more extreme than any technology could ever produce, and they are telling us things. Broadcasting their secrets in pulses of light and radio waves, in bursts of X-rays, in ripples of spacetime, in showers of antimatter, the signals are reaching us. We are catching them, we are measuring them, we are learning from them, but we are not done. The story of neutron stars is not a closed book. It is an ongoing investigation, a live mystery, with new clues arriving every time we point a telescope at the sky. Every pulsar is a data stream, every merger is a treasure trove of information, every glitch, every burst, every anomalous signal is a chance to learn something new. And every time we think we have the picture figured out, nature reminds us that the picture is bigger than we thought. That is what makes neutron stars so important. They are not just objects to catalogue and study. They are keys to understanding the universe at its most fundamental level. They are windows into physics we cannot access any other way. They are experiments we could never afford to build, running continuously, waiting for us to look closely enough to see what they are trying to tell us, so we keep looking, we keep listening, we keep measuring. Because somewhere in the timing residuals of a millisecond pulsar, or in the spectrum of a magnetar burst, or in the gravitational wave signal from a merger, or in the mysterious 22-minute pulse from an object that should be dead, there is an answer. An answer to a question we have been asking for a century. An answer that will rewrite the textbooks, shift the paradigms, and push the boundaries of what we thought was possible. Neutron stars are not the end of the story. They are the beginning of the next chapter. The chapter where we finally understand what matter does when you squeeze it to its absolute limit. Where we finally unify gravity and quantum mechanics. Where we finally detect dark matter and figure out what it is. where we finally map the full range of phenomena that the universe allows and that nature, in its infinite creativity, has scattered across the cosmos for us to find. That chapter is being written right now, in observatories scattered across the world, in satellites orbiting Earth, in computer clusters running simulations, in conference rooms where researchers debate the implications of the latest data, and in the minds of the scientists who have dedicated their careers to understanding these strange, dense, powerful, impossible objects that refuse to be anything other than exactly what they are. Neutron stars, the densest stable objects in the universe, the loudest beacons in the gravitational wave sky, the forges of the heaviest elements, the laboratories of extreme physics, and the messengers from a regime of nature that we are only just beginning to understand. So here we are, staring at a teaspoon of matter that weighs as much as a mountain, timing radio pulses from objects spinning hundreds of times per second, detecting gravitational waves from collisions so violent they forge gold, watching antimatter stream into space from a pulsar we cannot even see in visible light, measuring explosions that rise and fall faster than any supernova ever should, and trying to explain a signal that repeats every 22 minutes from a dead star that refuses to stay quiet. Every single one of these phenomena pushes physics to its edge, not past the edge, right up against it, close enough that the approximations break down and the equations start giving answers we do not quite trust. That is where neutron stars live. In the gap between what we think we know and what nature is actually doing, the density alone should be enough to break our models, 600 trillion times denser than water. Dense enough that space itself warps into a steep well you cannot climb out of. Dense enough that time runs slower at the surface than it does in orbit. Dense enough that we still do not know whether the core is made of neutrons or quarks or something stranger we have not named yet. And yet they are common, 100 million of them scattered across the Milky Way, most invisible, most silent, a few loud enough to be detected across the galaxy, a handful